table tells us to do is to take our first 10,000 VAs at 100%. Then we take that remainder and multiply it by 0.50. And then we can't forget to add the two back together. We take the 10,000 that we set to the side, we take the new reduced load, we add them together, and we get 27.5, and we select B. Great job. Hey everyone, welcome back. I am the Electrical Code Coach from electricalexamcoach.com, and this is lesson 5.2 in our video series. We're going to be in section 220.14, and we're going to be doing a good overview and a great foundation of commercial load calculations. Later in the program, if you'd like to do some more obscure, more rare commercial load calculations, you'll have the opportunity to do that as well. Let's get to it. All right, y'all, that's it for this lesson. You can head over to electricalexamcoach.com to unlock the pro version and the unlimited testing center. We also offer our full program on USB drive and DVD, so you can watch it offline and without commercials virtually anywhere. It also includes the MP3 files of all the lessons, so if you just want to listen to them as you drive down the road or while you're on the job site, you can do that. You can check out all that in the link in the description below. Most importantly, I want you to know that I offer 100% free coaching in life and in business. Just email me at electricalcodecoach@gmail.com. I just want to see you guys win. Let's get to it. I'm going to start out with learning about calculating DC total resistance of series circuits. Now, this is a very basic DC fundamentals course. This is not a DC fundamentals course. You could teach an entire 10-week course on DC fundamentals. I really encourage you, get familiar with that in your career. I'm just going to teach you some basic things on some questions that you may face on your examination. If you look at this circuit here, they're both the same picture. If you look at it, you have the battery symbol there, and we're going to go with conventional flow, saying it flows from the positive through the resistors to the negative. Electron flow would be from the negative to the positive. But our example here shows it from the positive, going through the resistors, coming back, through the negative. We're going to learn how to calculate total resistance of DC circuits. We're also going to learn how to calculate voltage drop across the DC circuit. The total resistance of a series circuit is equal to the sum of the individual resistances. RT, which just means resistance total, is equal to R1 plus R2 plus R3, and so on and so forth, however many resistors you have. We have a 12-volt battery in this case. We have 3 ohms on R1, 3 ohms on R2. So this is going to give us an RT of 6 ohms. So RT is equal to the total of all the resistors. In this case, R1 is 9 ohms. R2 is 4 ohms. So RT is going to be 13 ohms. Now let's learn about voltage drop of series circuits. First, we must calculate what the amp draw is on the circuit. If we know the voltage in the resistance, how could we calculate the amperage? We learned in week 2, part 1 about Ohm's law. First, we must get the total resistance and then apply Ohm's law. So in this case, it is 9 plus 4. It's going to be 13 ohms. So what we do is we set up our formula so we remember, and we plug in the knowns. In this case, we know that it's a 12-volt circuit. We got 13 ohms of resistance. All we must do now is to divide 13 up into 12, and that's going to give us our amperage. In this case, it's 0.923 amps. Second, we must use Ohm's law again to find the voltage drop across any given resistor. The voltage drop is going to be equal to R1 multiplied by I, and voltage drop of a resistor 2 is going to be equal to that resistor multiplied by I. Because remember, we're just trying to find the voltage drop. So E equals IR. Just plug in the knowns. In this case, we know the I and we know the resistance, and we're looking for the voltage drop. So we just multiply those two together. On this other side here, we just plug in the knowns, and we know the amperage and the resistance, and we just multiply that, and that's going to give us the voltage drop. So the voltage drop of R1 is 8.3 when we did our multiplication, and the voltage drop of R2 is 3.7. Okay, a quick recap. The voltage drop of R1 is 8.3. The voltage drop of R2 is 3.7. 8.3 plus 3.7 is going to equal 12 volts. The voltage will be equal to the sum of the voltage drop across all resistors, and that's how you double check your work. Now we're going to learn about calculating DC total resistance of parallel circuits. We're also going to learn about calculating voltage drop across an individual resistor in a parallel circuit. How many of you have already studied parallel RT questions in the past? The total resistance of a parallel circuit is expressed in this formula. R total is equal to the reciprocal of R1 plus the reciprocal of R2 plus the reciprocal of R3 and so on and so forth. To get the reciprocal of a number, you will just divide that number up into 1. What we're going to do is first get the reciprocal of each resistor, then take the reciprocal of that number, and that is going to give us the resistance total. This is another way to look at the formula. The reciprocal of R total equals the reciprocal of each one of those numbers. So that's another way to look at it. Okay, so we have 6, 3, and 9 as our resistors. So what is the total resistance of this parallel circuit? I want to note out right away that we have 4 options here in our question. The answer is always going to be smaller than the smallest resistor in the circuit. So if you're in your testing center and you get a question like this, we can tell right away that A and B are not going to be correct because the total resistance of a parallel circuit is going to end up being smaller than the smallest resistor. That's an easy way to figure that out. So now if you had to guess and you forgot the steps, you had a 50-50 shot. Just select C or D if you couldn't remember, and you got a 50-50 shot of getting the question right when you're in the test. Remember, always mark an answer on your test as correct. Even if you're just taking a total guess, you can mark it to come back later, but always put an answer because if you run out of time, you got a 1 in 4 shot of getting it right. Take our 1 divided by 6 plus 1 divided by 3 plus 1 divided by 9. Go ahead and do that on your calculator now. Pause the video if you need to. If you took the time and worked that out, it is going to give you 0.611111. But we cannot stop there. We must then take the reciprocal of that number. So we must then divide 1 by that number. So we take 1 and divide it by 0.611111. The question is how many of those ones do you put? What you do is go ahead and put the 1 divided by whatever the number is, and then type it in as many times until you get an answer that's close to one of your choices in your question. So in this case, we keep typing it in until we get 1.636, which is going to allow us to round up, and that's going to give us 1.64. I'll point this out that the testing center is not going to put them that close that if you did not round up or down, you're going to get the answer wrong. If you notice in our question, D is one whole number larger than that, you're going to be okay there. So just type it in until you feel comfortable with one of the answers that's represented. And then we rounded up and we selected C. Let's do another one. What is the total resistance of this parallel circuit? We look right away and we see that our smallest resistor is 2, so we know right away that C and D are incorrect. It's going to be either A or B. So let's move forward. So we take 1 divided by 2 plus 1 divided by 8 plus 1 divided by 10. We cannot stop there. We must then divide 1 by that number. That is going to give us 1 divided by 0.75. And that is going to give us 1.3793. We're just going to round up to 1.38. If you have chose to go with our testing center, we're going to have these questions on there. We also have detailed answers on how to work through the questions.
Hey everyone, welcome back. I am the Electrical Code Coach from electricalexamcoach.com. And this is lesson 5.4 in our video series. And in this lesson, we're going to be learning all about voltage drop. Let's get to it. If you were to do an internet search for a voltage drop formula, you would likely find this one right here. Voltage drop equals 2 kDi over C mil. And that is an excellent formula. And it's actually the one that I use. But I've rearranged it so it's easier to remember. I do it like this. 2 kid over C mil. Easy to remember and easy to plug in. And what this is, just like previously in the program, this is implied multiplication. So it's going to be 2 multiplied by K, multiplied by I, multiplied by D, divided by C mils. Now let's learn what each one of these individual pieces mean. 2 is going to be our constant multiplier for single phase. If we're doing 3-phase, we're going to use 1.732 as our multiplier. K is going to be the K factor. And I want you to think of it like a multiplier for your wire. For copper, it's 12.9, and aluminum, it's 21.2. Don't worry about remembering all this. If you're able to bring in uglies into your test, it has it in there. Your state might allow you to write inside your book. You can just write it in there. And if you have to do it like I did, you'll just go into the exam, and the first thing you'll do is write it down on your scratch piece of paper. I is your current in amperes, and D is going to be your distance. And you don't have to put it both ways. It's whatever distance the question says, you can plug it in one time. That's why I love this formula. And the C mills are going to be the circular mills of the wire. And we're going to teach you how to look up those. To find the C mills of a wire, we need to head to Chapter 9, Table 8. It's toward the back of the book in the Chapter 9 tables. Go ahead and head there now. When we get there, we find that there's a lot going on with the table, but just like every other table, we only need to focus on what we need to focus on. On the left-hand side, we're going to find our size of wire, and you'll notice all of your familiar friends, 14, 12, 10, then it goes down into larger numbers like 3/0 and 4/0, then it goes into the KC mills, and that's where we get those circular mills from, 250, 300, 350. In the next column over, we need to be sure to be in the area section because that's where we're going to get our circular mills value. Each wire has a circular mills value. And you'll notice for the first few wires that there's 2 sets of 12, 2 sets of 14, 2 sets of 10. But if you look over, the circular mills are the exact same size. So don't worry about if it's solid or stranded. Just go over to the circular mills. Make sure that you're in the area section under circular mills, and you'll find your value. You'll notice when you get down to 4/0 that the values stop. And the reason is because the left-hand side of this table, the 250, 300, and 350, are already showing you what the circular mills are in KC mills. So we have 250,000, 300,000, 350,000. So once you get past 4/0, you're going to get into 250, 300, 350, and all you have to do is add on the 3 zeros. What is the voltage drop of a 200 amp circuit using 4/0 copper conductors that is 225 foot long on a 120, 240 volt system? Step 1, we're going to write down our formula. I like to physically write it down on the piece of paper so I can go through one step at a time. Then I'm going to draw a large division line so I can put my inputs that need to be on top and then go look for my C mills. Let's start with 2. Is this a single phase or a 3-phase service? Well, this one is single phase, so it is going to be 2. Then I like to go ahead and put my X down for multiplication so I don't get my numbers mixed up. Then let's go to the K, and that's going to be dependent on the type of conductor. And in this case, it's copper. So the K factor for copper is 12.9. Now we need to look at I, which is current. We put down our X for our multiplier. We go to our question, and it's a 200 amp circuit. So we're going to put 200 down. Then we put our multiplier, and now we need to look for D. Well, our D is 225 foot, and we put that down. Now we need to find our circular mills. And for that, we're going to be looking for 4/0 in the table. When we head to Chapter 9, Table 8, we're going to start on the left-hand side and come down and find 4/0. Then we're going to cross over and we're going to find that it's 211600. Anytime it's a long number like that, I don't try to figure out my thousandths or tens, or I just say 211600 and I write that down. Then I write that down right under here. Now all we have to do is go to our calculator and plug it in. And all we have to do is plug in our values. We take 2 multiplied by 12.9 equals multiplied by 200 equals multiplied by 225 equals, and then we divide that by 211600. And it's as simple as that. That lets us know that we have a 5.48, which we would round up to 5.5 voltage drop on this circuit. And we select B. Great job. That's the end of lesson 5.4. You can head over to electricalexamcoach.com for more practice questions and lessons like these. Let's get to it. Hey everyone, welcome back. I am the Electrical Code Coach from electricalexamcoach.com. This is lesson 6.1 in our video series. Today we're going to be learning all about box fill. We're going to be in section 314.16, and we have two primary tables that we're going to be using. The first one that we're going to cover is 314.16a. Let's get to it. On the left-hand side is going to be our box size in inches. The next column over is going to be the type of box, and there are several different types of boxes. The first one is going to be the round octagonal box. A round box is truly circular, and the picture listed here is actually an octagonal box. I want to give a shout out to homedepot.com. It's where I snagged all these pictures. The next three lines you'll notice say square. And these boxes are true 4-square boxes. They're 4 by whatever the depth is. And if you look back over here to your dimensions where the box size in inches is listed, this box states that it's a 4 by whatever the depth is. There are 3 different depths. The next 3 lines you'll notice say square as well, but its dimensions are a little bit different. It says 4 11/16 by 4 11/16 by whatever the depth is. Down below there start your device boxes in all different shapes and sizes. Finally, we come to our masonry boxes. Listed below there, you're going to see different type of raised covers, which also give you a little bit more cubic inch volume inside of your box. The next column that we need to pay attention to is this middle one right here. Now, in the NEC, it actually says a minimum volume, which is kind of deceptive to the installer because it's actually your maximum volume that you're allowed to fill that box. And it's listed in cubic inches. That's all we're concerned with. We're not concerned with any metric designators inside of this table. We want to be dealing with cubic inches. And the reason it's cubic inches is because we have 3 different measurements. We have 4 by whatever the depth is. In this column, you're going to find the maximum that you're allowed to fill each box. Then when we come over here to the far right of the table, it's one of my favorite pieces. It's actually like a cheat sheet. If all of your wires are of the same size, you can use this part of the table and make it very simple on yourself. First thing you'll do is you'll come over and find your gauge of wire. Then you'll come over here and find your type of box, and then come over and tee off with how many wires can fit inside of that box. It's very simple. Now let's look at the second table that we're going to be dealing with for box fill. And it's right below there. It's 314.16b. And this one's very simple to understand. On the left-hand side is our conductor size. And on the far right-hand side is going to be our cubic inch volume. Every box can only handle so many wires and devices. And that's what we're going to learn in this lesson here today. Each box has so many cubic inches that you can fill, and each conductor and device takes up so many cubic inches of that box. Now, let's do some practice questions and get to it. What size round octagonal box would you select for 9 number 12 conductors? For this one, we're going to be using table 314.16a. We're going to start here and we're going to find our gauge of wire. Then we're going to come down and we're going to find a box, making sure to cross over and double check that we don't crest over into a different style box. We want to stay in the round octagonal. We find our conductors, we find the one that fits it, we slide over and double check ourselves, and we're going to select A. Great job! What size round octagonal box would you select for 7 14 gauge conductors? We're going to head to table 314.16a. We're going to start here on the right-hand side and we're going to find our gauge wire. Then we're going to come down and find a box that fits it and be sure when we cross over that we stay in the right category of box, and we're going to select C. What size 4-square box would you select for 8 number 8 conductors? We head to 314.16a. We're going to start here on the right-hand side and we're going to find our size wire. Then we come down and make sure that we're in the right type of box. We cross over and we're going to find that it's A. How many number 10 conductors can you fit inside of a 4 11/16 by 1.5 inch square box? It's the same process, just looking at it differently. we're going to go ahead and come to our table, 314.16a. We're going to find our gauge conductor. We're going to come down and find our box. Make sure we cross back over, and we find that we can fit 11 inside of this box. How many number 8 conductors can you fit inside of a 4 by 2 1/8 by 1.5" device box? We head to 314.16a. We're going to find our gauge wire. Then we're going to come over and find our type of box and size, make sure we do everything correctly, and we're going to find that it holds 3. What is the maximum cubic inch volume for a 3 3/4 by 2 by 2 1/2 masonry box? For this one, we're going to head to 314.16a, and we're going to use that middle column, that volume column, and we want to find out how many we can do. We come down, we look very closely, and we find that it's 14 cubic inches. This is very important that we understand this process before we move on into more complex box fill calculations. What is the maximum cubic inch volume for a 4 11/16 by 1.5" square box? We're going to use the same process. We head to our table. We're going to go to that volume column, and we're going to come down and find our correct type of box, and we're going to find that it's 29.5 cubic inches available area to fill. How many more number 10 conductors can you fit inside of a 4 11/16 by 1.5" square box that already contains 6 number 10 conductors in it? Well, since both of these are of the same size, we can just do some simple math. First, we have to find out how many the box holds at all. And we go in and we find that it holds 11. Then we have to do some simple math. We already have 6 conductors, so we take our original 11 minus 6, and it lets us know that we can put 5 more inside of that box, and we select A. How many more number 12 conductors can you fit inside of a 4 by 2 1/8 by 2 1/8 device box that already contains 5 number 12 conductors? For this one, we're going to head back to our table 314.16a. First, let's find out how many wires it can hold originally. It can hold 6. We already have 5, so we take 6 minus 5 equals 1, and we can put 1 more conductor inside of this box. What is the cubic inch volume for a number 6 conductor? For this one, we're going to head to 314.16b. We're going to start here on the left-hand side of the table and find our size conductor. Then we're going to come over and we're going to cross over to our cubic inch volume, and we're going to select D. Great job. What is the cubic inch volume for a number 12 conductor? Head back to 314.16b, start on the left-hand side and find our size conductor, then cross over to the cubic inch volume, and it's stating that for every number 12 that's in that box, according to the count, which we're getting ready to learn, takes up 2.25 cubic inches of that box. Let's get to it. What is the total cubic inch volume you would calculate for 4 12-gauge conductors and 3 14-gauge conductors? First thing we're going to do is head to our table. Now we have to do some simple math. Let's grab all of our 12-gauge conductors first. We have 4 of them. Multiply it by 2.25. That equals 9 cubic inches. Now let's snag our 14s. We take 3 multiplied by 2, and that gives us 6 cubic inches. But now we can't forget to add them back together. Total it all up, and these conductors are taking up 15 cubic inches of this box, and we're going to select C. What is the total cubic inch volume for 3 10-gauge conductors and 5 8-gauge conductors? We head straight to our table. We do some math here. We bear out the 10-gauge conductors. Then we bear out the 8-gauge conductors. We total those two back together, and we find that it's taking up 22.5 cubic inches, and we select B. What is the smallest device box you could use to fit 4 12-gauge conductors and 3 14-gauge conductors? For this one, we're going to be using tables A and B. Let's start over here in table B and get our total count. Then we'll go to table A and find which box fits it. We do the math on our 12-gauge conductors. We do the math on our 14-gauge conductors. These conductors are taking up 15 cubic inches. The code wants to know the smallest box that will fit it. So we come over here to our middle column, the volume column, and we slide down until we find a device box that just fits it. And we're going to find that it's a 3 by 2 by 3 1/2. What is the smallest round octagonal box you could use to fit 3 10-gauge conductors and 3 12-gauge conductors? For this one, we're going to be using both the tables again. Let's go ahead and bear all of our math out. And we find out that these conductors are taking up a total of 14.25. Now let's head over here to table A and go down the volume column until we find the right type of box, which is right up here at the top. The round octagonal boxes. Find the one that fits, and it's a 4 by 1.5 inches. Great job. Now let's learn about the rules for box fill. We're getting ready to cover a lot of ground, and this is something that you have to master. But don't feel like that you have to master it in one pass. Watch this part of the video over and over until you thoroughly understand it. We're going to learn how to count conductors now for our box fill calculations. We have to accommodate for each wire and then also for the different devices and fittings that we use out in the field. We're not going to be dealing with equipment grounding conductors at first. We're going to calculate those separately at the end of this slide. So now we're dealing with only neutrals and hots. Each conductor counts as 1 of whatever gauge it is. So each 12 counts as 1, each 10 counts as 1, whatever gauge wire it is. Each conductor that passes through the box counts as 1. So even if it doesn't terminate or splice inside that box, if it's passing through that box, it counts as 1 each. Each internal clamp only counts as 1 total based off the largest conductor that's in the box. Let me show you what I mean. This is an internal clamp. The clamping mechanism is inside the box. Well, it's taking up some of my space, so we have to account for it somehow. What this code is stating is it doesn't matter if I have 1 or 5 of these clamps, we're only going to count it as 1, and it's going to be grouped with whatever the largest conductor is in the box. Meaning if I have 12 and 10-gauge conductors inside that box, this internal clamp would count as 1 10-gauge conductor. All of the fittings we're going to convert over to conductors, then the conductors we're going to convert over to the cubic inches, and you'll know more of what that means as we go through this lesson. This is an external clamp because the clamping mechanism is on the outside of the box, and we don't have to count those at all for box fill purposes. Next, each stud or hickey that is present in the box shall count as 1 total based off the largest conductor that's in the box. Now, these are really old words, probably from the 30s if I had to imagine, but they still use them on examinations today. And this is what we're talking about. Imagine that we're hanging a chandelier. This we would call the stud or the nipple. Or, this would be the nipple, this would be a nipple. But they're calling this the stud and this a hickey. And they still use this terminology on exams today, so you definitely need to understand. In this scenario here, in this picture, the stud would count as 1 of whatever gauge was in the box that was the largest, and the hickey would count as 1 of whatever gauge was in the box that is the largest. And we're going to do lots of practice, so don't worry about it. Now we need to account for device straps and yokes. What the code states is that for each device strap or yoke, it's going to be counted as 2 based off the largest conductor that's connected to the device. As we learned earlier in the program, this is a device yoke or what we call a device strap. So each one of those, and how I like to think about it, is each gang of a box. If you have a single gang box, 2 gang box, or 3 gang box, each gang is going to count as 2 based off the largest wire that is connected to the device. So if I had a box that had 12 gauge on one switch and 14 gauge on another switch, the first switch would count as 2 12s and the second switch would count as 2 14s. Now let's deal with equipment grounding conductors. Let's deal with the 2017 first. If you are on the 2017 code, this is how you deal with equipment grounding conductors that are in the box. It's only counted as 1 total based off the largest conductor in the box. Meaning it doesn't matter if you have 10 equipment grounding conductors, they all only count as 1 for your count total, and it's based off the largest conductor that's in the box. So if I have 10s and 12s, it's only going to count as 1 number 10. Now in the 2020 and in the 2023, it's a little bit different. Up to the first 4 conductors, it's going to count as 1.
then for every one that is past 4, you're going to increase it by a 1/4 inch volume. And we're going to do some practice questions with these. Just let that soak in, and when we get to the practice questions, we're going to expound on it more. If you're still on the 2017, when I come to this part of the lesson today, I want you to just fast forward through it. You don't need to learn it. It will just confuse you. 2017 will come first, and the questions will state what year I'm dealing with. Then when we get to the 2020 and the 2023, I'll let you know, and that way you can learn your respective lesson. Let's get to it. What is the total cubic inch volume you would calculate for a light box that contains 3 12-gauge conductors with 1 stud and 1 hickey present in the box? For this one, we're going to go to table 314.16b. We know that each 12 is 2.25 cubic inches. Now let's count our conductors. We know that we have the 3 number 12s originally, but now we have to deal with the studs and the hickeys. Our code states that for each stud and each hickey, they count as 1 each based off the largest conductor that's in the box. In this case, we only have number 12s, so they're going to be grouped with the 12s. So that lets us know that we have a total of 5 number 12s. That's what I meant by we're converting everything back to conductors, and then we can do our multiplication. We take those 5 number 12s, multiply it by the cubic inch volume for 12, and we end up with 11.25 cubic inches, and we would select C. What is the total cubic inch volume you would calculate for a light box that contains 3 number 12 gauge conductors, 3 14 gauge conductors, and 1 hickey present in the box? We'll head to our table. We know that each 12 is 2.25. So you always deal with the largest conductors first. And the reason is because your fittings are likely going to be grouped with the largest conductors. We know that we have the 3 number 12s, but now we got to deal with our fittings. In this case, we have 1 hickey. Each hickey counts as 1 based off the largest conductor that's in the box. And what we're going to do is group it with the 12s. We have the 3 original conductors, the 1 fitting. We have 4 number 12s. We bear that math out and end up with 9 cubic inches. Now let's deal with our leftover conductors. We have 3 14 gauges. We take and bear all that math out. Then we total it together and we end up with 15 cubic inches that all of this is taking up in this box. This is something that you'll have to take your time and master. One of my favorite sayings is, you don't wake up on that level. You don't wake up understanding this. You don't watch the video once and get it. If it were that simple, anybody can do it. I hope it's been very easy for you to understand up into this point, but for you to truly master it, you got to get after it. What is the total cubic inch volume you would calculate for a box that contains 8 number 12 gauge conductors and 2 single pole switches in a 2-gang box? We look at 314.16b. We know that each number 12 is 2.25. Let's go ahead and count our conductors. Each device yoke counts as 2 based off of whatever wire is terminating to the device. We know we have 8 original conductors, and we only have 1 size wire, so we know it's going to get grouped with the 12s. And each one of those devices counts as 2, so we end up with 4 more number 12s, which gives us 12 12-gauge conductors. Now we take and do our math, we end up with 27 cubic inches, and we select B. What is the total cubic inch volume you would calculate for a box that contains 8 12-gauge conductors terminating to 2 single pole switches, 6 14-gauge conductors terminating to 2 single pole switches in a 4-gang switch box? This looks like a tough question, but I know that you can do it. First, we're going to head to our table so we can get our values. We know what each 12 is, and we know that each device yoke counts as 2 based off the largest wire that's terminating to the device. Let's go ahead and deal with our 12s. We know that we have 8 conductors and 2 devices for those 12s, so each one of those devices counts as 2 more, giving us a total of 12 12-gauge conductors. We take and bear the math out, and we end up with 27 cubic inches. Now we just do the same for the leftover devices. We have our 6 original conductors, and we have 4 more based off of our count, because remember, it's based off the largest wire that terminates to that device. We take and bear that math out, total the 2 together, and end up with 47 cubic inches. Let's get to it. What is the total cubic inch volume you would calculate for a box that contains 3 internal clamps and 4 12-gauge conductors? We head to our table. We know what each 12 is. All internal clamps count as one total based off the largest conductor in the box. We only have one size wire in the box, so we're good to go. We take our 4 original conductors plus our 1 clamp count, and that equals 5. We bear our math out, and we select C. Now let's deal with equipment grounding conductors. In the 2017, all equipment grounding conductors just count as 1 based off the largest conductor in the box. 2020 and later, all equipment grounding conductors count as 1 based off the largest conductor in the box up to 4 conductors. So 4 conductors and under count as 1 total. But when you have over 4, there's going to be a 1/4 inch volume increase that's going to be added for each additional equipment grounding conductor after 4. I'm going to teach you how to do it one step at a time. What is the total cubic inch volume you would have for a box that contained 2 hots, 2 neutrals, and 2 equipment grounding conductors, all of the 12-gauge persuasion in the 2017? Well, we know we're going to count our 2 hots, we know we're going to count our 2 neutrals, and all of the equipment grounds count as 1 total. We would have a total of 5 cubic inches. We do the math for 12-gauge conductors, and we end up with 11.25. Let's do one more quick practice for the 2017. We got 3 hots, 3 neutrals, and 3 equipment grounding conductors, all of the same size. We're going to take those 3 hots, the 3 neutrals, and then all of the equipment grounds count as 1 total based off the largest conductor that's in the box. That gives us 7. Now we bear our math out, end up with 15.75, and we select D. Let's go ahead and do one more for the 2017. We have the total cubic inch volume, and we have 3 12 hots, 3 12 neutrals, 3 14 hots, and 3 14 neutrals, and 6 equipment grounding conductors in the box. First, let's count our 12s, because that's what we're going to group all the equipment grounding conductors with, is the largest conductor in the box. We know we got 3 hots, we know we got 3 neutrals, and we're going to group all of those equipment grounding conductors, counting them as 1 with the largest, which happens to be 12. We take and bear that math out. Now let's deal with the 14s. We had 3 hots, 3 neutrals, don't have to deal with any grounds, they've already been dealt with. We take and bear that math out, total the two together, and we end up with 27.75 cubic inches. Now let's move on to the 2020 and the 2023. What is the total cubic inch volume you would have for a box that contained 7 equipment grounding conductors, all of the 12-gauge persuasion in the 2020 and the 2023? I left out all other conductors because you're going to use the same rules in that after you do this calculation, you group it with whatever the largest conductor is in the box, like you learned previously. What we're going to do is we're going to count the first 4 and count it as 1. And then a 1/4 inch increase for each one past 4. Sounds complicated. We're going to break it down very simply. We have 7 total, and we're going to minus 4 because those first 4 we counted as 1. So we have 3 left over, and we're going to take those 3 and multiply it by a 1/4, and that gives us 0.75. So we have a total of 1.75 conductors based off whatever the largest conductor is in the box. In this case, there's only number 12s. So we would take that 1.75, multiply it by the cubic inch volume for a number 12 conductor, and we end up with 3.9375 cubic inches for our equipment grounds. What is the total cubic inch volume you would have for a box that contained 6 hot conductors, 6 neutral conductors, and 6 equipment grounded conductors, all of the 12-gauge persuasion in the 2020 and the 2023? First thing we're going to do, we know we take the 6 hots and the 6 neutrals, and we're going to set that to the side. Now we got to deal with the equipment grounding conductors. We're going to, for the first 4, it's going to count as 1. So we need to figure out how many we are past 4. We have 6 total minus that 4. That means we are 2 past 4. For each one of those, it's going to be a 1/4 inch increase. Take 2 multiplied by 0.25, that equals 0.50. Then we have our 1 original. Then we have 0.50 add-on, so that gives us 1.50 grounds. We need to take and add that back to the 12, so we take our 12 plus our 1.50. Then we multiply that by the individual volume for a number 12, which is 2.25, and we end up with 30.375. Let's get to it. All right, y'all, that's it for this lesson. You can head over to electricalexamcoach.com to unlock the pro version and the unlimited testing center. We also offer our full program on USB drive and DVD, so you can watch it offline and without commercials virtually anywhere. It also includes the MP3 files of all the lessons, so if you just want to listen to them as you drive down the road or while you're on the job site, you can do that. You can check out all that in the link in the description below. Most importantly, I want you to know that I offer 100% free coaching in life and in business. Just email me at electricalcodecoach@gmail.com. I just want to see you guys win. Let's get to it. Hey everyone, welcome back. I am the Electrical Code Coach. Let's go ahead and dive right into pipe fill. This first lesson is going to deal with if all the conductors are of the same size and insulation type, meaning if they're all number 12s and THHN. The next lesson, lesson 7.2, will deal with if we have different sizes of conductors and different insulation types, meaning if I have 10s and 12s inside of the same conduit. Let's go ahead and learn about the table that we'll use if they are all of the same size. We're going to use Annex C. And if you've tabbed your code book, you have an Annex C tab. And if you haven't tabbed it, you can just follow along. If the conductors are all of the same size and insulation type, we get to use like a cheat sheet in Annex C. It's one of my favorite tables in the code book. You will not use this table if the conduit is 24 inches or less. Now the code book uses the term nipples, but I want you to imagine in your mind, anytime the conduit is 24 inches or less, you're not going to use Annex C. You're going to use the method that I'll teach you in lesson 7.2. You can head to page 712 of the 2017 and page 729 of the 2020. This video is 2023 compatible. You'll have to get to your page number for Annex C, and then you can follow along. So when we get to Annex C, the beginning of it, I call it the Start Here page, because every time you're doing one of these calculations, you're always going to start here if you're using Annex C. Now, when we get there, we always read the black bold heading to make sure that we're in the right table. Great, I feel like we're in the right table. Now, when we head over to the left-hand side, we're going to find types of conduit. And the first one that we come to is EMT, electrical metallic tubing. Now let's look at the second one that we come to. It also is EMT. So what is the difference? And that's one of the most important distinctions that we have to watch out for with Annex C. The first version of the table, if you'll notice next to the C1, there is no A symbol. The A symbol signifies compact conductors. There are several different types of conductors out in the industry. Some of them are concentric, but the ones that are compact are bound a little bit tighter, and you can actually fit more of those inside of a pipe legally. But for your normal pipe fill questions, they're not compact conductors. Matter of factly, unless it says the word compact conductors, you will never assume that they're compact conductors. And you do not want to use the A versions of these tables. So when you go to the first one, it says C1 EMT. And then the second one is C1A. That's letting you know it's a compact conductor table. Now let's imagine that we did want to go to EMT. Now to slide all the way over, if we look at our far right-hand column, we're going to find that that is our page number. And for this table, you're definitely going to want to use a straight edge. Do not trust your eyes on this one. This is not a one-point question, meaning that it could count as multiple points on your exam. These are more difficult questions, and you don't want to make a simple mistake by not crossing the page correctly. One way that guys eliminate this is they will actually highlight every one that is not in A table. So they'll highlight C1, C2, C3, and they'll use a straight edge and highlight all the way across to the page number to shave off just a few seconds while they're testing. Remember, part of this is strategy, and it's beating the clock. You've only got a few minutes to answer these questions. So doing some strategic highlighting can really save you a lot of time on the back end. Now that we've learned about the Start Here table, let's actually go to where we find the values. So let's imagine that we are using EMT conduit. So we're going to start on the left-hand side. We're going to find our type of conduit, being sure that we're not in an A version of the table. Then we use a straight edge and cross over and find the page number. Go ahead and flip to that page number now. And when we get to that page, we're going to find a brand new table, and we're going to break it down piece by piece. The main thing that we have to watch out for with this table is that we always read the black bold heading when we get to that section to make sure that we're in the right table. As you'll find throughout the entire NXC, all of these tables look identical. The only difference is the title of the table. So every time I even flip a page in NXC, if I have to flip a page, I stop and make sure that I haven't started off into a new table. Because the difference between you being in this table and that table is just one page, and there's no difference in the table look and feel. So just make sure that you're always reading the table to make sure that you haven't, gone off into the A version of the table, which comes right after the regular version, and that you haven't crossed off into another type of conduit. Starting on the left-hand side, we're going to find our type of insulation. And this is where we find some familiar friends. RHH, RHW, THHN, THWN-2, and that's going to be our type of insulation that our wire is coated. And then in the second column is going to be our size of wire. Now, you may find when you're looking that you find your type of insulation, but you don't find your size wire over there in the wire column. That's okay. Just start over until you find the type of insulation again, and then you'll cross over and eventually find your size wire. Then once you find both of those, you'll come across the top of this table, and you'll see your trade size of conduit. All of our familiar friends, 1 inch, 2 inch, 3 inch, and so on and so forth. Once we line all three of those up, all we have to do is come down and tee off, and we find how many wires can fit inside of that conduit legally. I love this table because they've done all of the hard work for us that I'm getting ready to teach you in lesson 7.2. How many THW, number 10, can you fit inside of a piece of 1 inch rigid metal conduit? The first question we ask ourselves is, are they all of the same size and insulation rating? They are, so we're going to head to Annex C using our Annex C tab. When we get to the Annex C Start Here page, we're going to start on the left-hand side until we find our type of conduit, which was rigid metal conduit. Then we're going to come down and make sure that we don't select the A version of that table, and we're going to use our straight edge or our highlighting that we've done, and we're going to go to the page number. When we get to that page number, we're going to read the black bold heading to make sure we're actually in rigid metal conduit and that we're not in the A version of the table. Then we're going to start on the left-hand side until we find our insulation type. Every time we flip a page, we're reading that heading to make sure that we're not starting off into a new table or a new version of the table. Then once we find our insulation type, we're going to cross over to the size of wire. As long as our size of wire is listed there, we're going to come across the top to the size of conduit. Then we come down and we tee off with how many wires can fit inside that conduit. And we find that we can fit 14 of them. Great job. How many more THWN number 10 can you fit into a piece of 3/4 inch EMT that already contains 4 THWN number 10s? The first thing we're going to ask ourselves, are they all of the same type and insulation? They sure are. So let's head to Annex C. When we get there, we're going to start on the left-hand side and find our type of conduit, being sure not to select an A version of the table. Then we cross over and find our page number. When we get to the actual table, we're going to read the black bold heading to make sure we're in the right table. Then we're going to find our type of insulation under the insulation column, find our wire size, and then come across the top to our size of conduit and tee off with our answer. And we find out that we can fit 10 originally. But our question states that we already have 4 of them in the pipe. So all we have to do is do a little third grade math. We take 10 minus 4 equals 6, and we find out that we can fit 6 more inside of this conduit. Great job. How many 1/0 THW conductors can you fit inside of a piece of 2.5 inch Schedule 40 PVC? Are they all of the same size and insulation? Yes, so we're going to head to Annex C. When we get there, we're going to start on the left-hand side until we find our type of conduit, being sure not to select the A version of the table. Then we come across and find our page number. When we get to the table, we always read the black bold heading to make sure that we're in the right table. Starting on the left-hand side, looking for our type of insulation. When we find it, we go to our size of wire,
come across the top until we find our conduit size. Then we're going to come down and tee off and find that we can fit 8 more conductors inside of this conduit. Great job. How many more 2-aught THHN conductors can you fit inside of a piece of 3-inch Schedule 80 that already contains 5 2-aught THHN conductors? Well, the first question we're going to ask is, are they all of the same size and insulation? Yes, so let's head to Annex C. When we get to Annex C, start here, we're going to start on the left-hand side until we find our conduit, being sure that we're not in the A version of the table. Then we're going to come over and cross over and find our page number. When we get to the actual table, we're going to start first and make sure that we're in the right table by reading the black bold heading. Then we start on the left-hand side and find our insulation type, find our wire size, then come across the top and find our conduit size, and come down and tee off with how many conductors we can originally fit. And it looks like we can fit 11. Now we have to minus the 5 that we already have, and that lets us know that we can fit 6 more of these conductors inside of this conduit. Great job. How many more number 10 THW-2 conductors can you fit inside of a piece of 3/4 inch Schedule 80 PVC that already contains 3 number 10 THW-2 conductors? The first question we're going to ask ourselves, are they all of the same size and insulation type? They are. So we're going to head straight to Annex C. When we get to Annex C at the Start Here table, we're going to start on the left-hand side until we find our type of conduit. Then we're going to verify that we're not in the A version of that conduit. We're going to slide over and find our page number. Then when we get to the table, we're going to read the black bold heading to make sure that we're in the right table. We start on the left-hand side and we find our insulation type. Then we find our wire size. Then we come across the top and find our conduit size. And we're going to find that our starting value is 7. We have to minus the 3 conductors that we already have, and that's going to let us know that we can put 4 more. All right, y'all, that's the end of lesson 7.1. You can head over to electricalexamcoach.com and check out our completely free version. But if you're really wanting to get your license and you're serious about it, really encourage you to check out our pro version, which will unlock all of the practice tests, quizzes, and all of the other pro features. That is really the recipe for getting your license. I am the Electrical Code Coach, and you can always email me at electricalcodecoach@gmail.com if there's any way that I can help you in life or business. Let's get to it. Hey everyone, welcome back. I am the Electrical Code Coach, and we're picking right up in pipe fill. This is lesson 7.2. So in our previous video, we learned that if the conductors are all of the same size and insulation type, we can just head straight to Annex C to answer all of our pipe fill questions. But when they're not, we're going to learn about what to do today. We're going to learn about Chapter 9, Table 4 and Chapter 9, Table 5. First, let's learn about Chapter 9, Table 4. It's on page 680 of the 2017. It's on page 696 of the 2020, and this video is 2023 compatible, so you find your page number for Chapter 9, Table 4. If you've used the Mike Colt tabs that we recommend, you're going to have a Chapter 9, Table 4 tab, and you can flip there now. Let's get to it. When we get to Chapter 9, Table 4, we're going to find that all of these tables look almost identical, and the only distinction is the name of the type of conduit at the top of the table. You'll notice that the very first one is EMT, and then it goes down to a bunch of familiar friends in conduit, our RMC, Schedule 80, Schedule 40, and all of those different types. If you get our pro version to the program, we have a video called the Strategic Highlighting video that will show you how to strategically highlight these tables to make them pop. Starting on the left-hand side of this table, we're going to find our size of conduit. We want to make sure that we are in the inches column. We're not dealing with millimeters. Then we have a bunch of different columns across the top. The first one is more than 2 wires. The second one is 60%, and that's going to be for nipples. Our 1 wire is 53%, 2 wires, and then the diameter of the pipe, and then the 100% total fill area. Let's break them down one by one. The first one that we come down is when we have more than 2 wires. So anytime we have 3 or more wires, we're going to use this percentage. It's the 40% fill column.
What it's saying is you're allowed to fill that conduit up to 40% of its capacity. And these values listed down below are going to let you know what that capacity is. So we'd start here on the left-hand side, find our tray size conduit, and then we would come over to our respective column. And that lets us know the total square inch capacity of this pipe that we are allowed to fill. In box fill, we use cubic inches, but in pipe fill, we're going to use square inches. And the next column over would be our 60% for nipples. So when we're dealing with nipples that are 24 inches or less, we're going to use the 60% fill column. So the question will ask, if we have a nipple of this size, how many conductors can you fit? First, you would come over to your size of conduit. Then if it was a nipple, you would come over here, you would grab that value, and that's how much space you have total to fill. Then the same thing here with one wire and two wires and the diameter and the area completely. Now you say, when would you ever have one wire? Well, a really good example is if you are doing a grounding electrode conductor. You might have one wire in a pipe. Also, this includes one cable. It'll be treated like one wire. So if you put one piece of Romex in there, you're actually going to use the 53% column here. And the same thing with two wires. It would be if you had only two wires, or if you had two cables in the conduit. Or if you had three cables, like 3 pieces of Romex, you would use the 40%. Now, we won't hardly ever use the diameter, but if you're ever asked a specific question, what is the diameter of such and such conduit, this is where you find all your information for conduits, right here in the Chapter 9 Table 4 table. I will say this, I have had this final column on an exam before, the 100% area. It will ask you what the 100% area of a conduit is. All you have to do is remember to come to Chapter 9, Table 4, find your type of conduit, slide over here to the 100%, and you'll be able to look it up and find that one easy. Let's get to it. Now that we've learned all about Chapter 9, Table 4, and that it's all about conduit dimensions, now let's head to Chapter 9, Table 5, and let's learn about the conductor dimensions. Just like with box fill, each conductor has a size that it is. It is a square inch size when you're dealing with pipe fill. And we're going to head over and find out how to find out that square inch value. Then we know all we have to do is divide, just like we did in box fill. When we get to Chapter 9, Table 5, it looks very similar to Annex C. But anytime we come to a table, we have to be careful to make sure we're in the right table. We want to make sure that we're in Chapter 9, Table 5, not in Chapter 9, Table 5A. Just like with Annex C, there is an A version of the table that is for only compact conductors. So we're going to head here and we're going to start on the left-hand side and find our type of insulation. Then we're going to cross over and find our wire size. Then we have to be careful here. We want to make sure that we're in the approximate area and that we're in the inches squared. We're not dealing with diameter for pipe fill, although there may be a time that you have a question that asks you for the diameter of a conductor. If that's the case, you would head here and it'll tell you the answer. But we're dealing with area when we're dealing with pipe fill. So we start on the left-hand side, find our type of insulation, find our wire size, and then find our approximate area in inches squared. Now, let's do some practice questions. Before we jump into the practice questions, let's go ahead and hit the major points. We're going to use Annex C when all of the conductors are of the same size and insulation. With dealing with equipment, grounding, and bonding conductors, they shall be included based off the actual dimensions of the conductor. It's not like we did in box fill. If there is a grounding conductor in that pipe, it counts 1 for 1, and all of them count. If you've got 10 of them, they all count. Conduit 24 inches or less shall be calculated from the 60% fill column. A combination of conductors of different sizes shall use the actual dimensions from Table 5 or 5A if they're compact conductors, and then we're going to use the dimensions of the conduits listed in Chapter 9, Table 4. And it's a little bit different than when we're dealing with load calculations. We're actually going to round up when it's 0.8 or greater. And I have one of those examples in our questions coming up, so you'll be a pro by the end of this video. Let's get to it. How many more number 12 THHN conductors can you install into a piece of 3/4 inch EMT that already contains 3 number 10 THHN conductors? The first thing we're going to do is we're going to find the total area that we have to work with. And to do that, we're going to head to Chapter 9, Table 4 for EMT. And when we get there, the first thing we do is make sure that we're in the right type of conduit. Then we're going to start on the left-hand side and find our trade size, and we go down to 3/4.
Then we're going to cross over to the more than two because our question deals with more than two conductors. So we're going to pull from the 40% column. And that's going to let us know that our starting available area is 0.213 square inches. Now we need to find what we already have, which is the number 10s. We're going to head over to Chapter 9, Table 5. And when we get there, we're going to start on the left-hand side and find our type of insulation. We're going to cross over and we're going to find our size of wire. Then once we find that, we're going to cross over to the approximate area. And each individual number 10 is 0.0211 square inches. Now that we have our conduit and our starting conductor, let's go ahead and write down our number 12s. That's the conductor that we're wanting to install. And then we'll be done with the code book, and all we have to do is some simple math. After we find that value and write it down, we can proceed. We're going to take and multiply our conductors that we already have. We have 3 number 10s multiplied by the value by a number 10, and that gives us this number. Now to figure out how much space we have left, all we have to do is take our total fill area, which was 0.213, subtract the number 10s, and then that lets us know we have 0.1497 remaining left to fill. In order to find out how many number 12s we can fit in it, all we have to do is divide. We take our available area left to fill, divided by the individual number 12, and we're going to find out that we can fit 11.255. In this case, it's lower than 0.8, so we're going to round down to 11 conductors, and we select D. Great job. How many 1/0 XHHW conductors can you install into a piece of 2.5-inch Schedule 40 that already contains 4 4/0 XHHW conductors? So the first thing we're going to find out the square inches of our pipe. For that, we're going to head to Chapter 9, Table 4, 4 Schedule 40. When we get there, we're first going to verify that we are in the right type of conduit. Then we're going to come over here to the left, find our size of conduit. Then we're going to come over to the 40% column because we have more than 2 conductors. And we're going to find that for this conduit, it's 1.878. Now we need to head to Chapter 9, Table 5 and find out the square inch values of our wires. When we get there, we make sure that we're in Chapter 9, Table 5 and not Chapter 9, Table 5A. Coming down the left-hand side for the type of insulation, then finding our wire size, then we come over here to the approximate area in square inches, and we find its value. Now that we have our conduit and our starting conductor, let's go ahead and write down what the conductor that we're wanting to install is. And it's 1/0 XHHW. Now we can start all over. We multiply by how many conductors that we already have. We have 4 multiplied by the value for a 4/0, and that gives us this number. Then what we're going to do is take our total area that we were able to fill and minus what we have, and that lets us know what we have remaining left to fill. Then all we have to do is divide. We take our remaining left to fill, divide by our individual 1/0, and that lets us know that we can fit 3.28 conductors. We are below 0.8, so we're going to round down, and we find that we can fit 3 more in the conduit. How many number 12 THHN conductors can you install into a 20-inch nipple of EMT that already contains 3 number 10 THHN conductors? First, we're going to find the square inches of our pipe. We found out previously that Table 1 tells us for nipples that are 24 inches or less, we are going to use the 60% fill when using EMT. So how we find out what the 60% is we'll head to Chapter 9, Table 4. First, we will verify our type of conduit to make sure we're in the right conduit. Then we're going to start on the left-hand side and find our size of conduit. But then we need to cross over to the 60% fill because this is a nipple. And we find that it's 0.320. Now we can finish the problem like normal. We're going to head to Chapter 9, Table 5 and find out the square inch value of our conductors. When we get there, we verify we're in 5 and not 5A. Then we're going to come down and slide on the left-hand side, come over to our size wire. Then we're going to come over to the approximate area, and we're going to find that it is 0.0211. We found out our pipe. We found out our starting conductor. Let's go ahead and write down the conductor that we're wanting to add while we're right here in the table. Now, all we have to do is multiply. We take our original conductors, which was 3, multiplied by its value, and that gives us this value. Then all we have to do is subtract from our starting value. Our starting value was 0.320. Now all we have to do is minus what we already have, and that lets us know that we have this much remaining left to fill. Then, to find out how many more we can fit, we simply divide. We take our available left to fill divided by the conductor that we're wanting to install, and that lets us know that we can fit 19.3. We're going to round down again, and we are going to select B. Great job. The next 3 sample questions are going to go a lot faster. It's assuming that you've already learned how to use these tables. I'm not going to be showing them on the screen. How many more 2-watt THHN conductors can you fit inside of a piece of 3-inch Schedule 80 PVC if it already contains 5 1-aught THHN conductors? Well, what we're going to do is we're going to go to Chapter 9, Table 4 and find our pipe. Then we're going to find the appropriate column based off of our number of conductors. And we're going to find that for 3-inch, here is the value. Then we're going to go find our type of insulation in Chapter 9, Table 5. Go ahead and get all of the values for conductors that are involved. First, we're going to take our known conductor, 1-aught, and we're going to take and multiply it by 5, and that's what we're already filling of this pipe. Then we're going to take and minus our total fill, minus what we already have, and that gives us our remaining left to fill. Then we take our 2-aught conductor and we divide it out, our remaining left to fill, by the conductor that we're wanting to install, and we're going to find that we can fit 7.4. Again, we're going to round down because it's less than 0.8, and we're going to select B. How many more number 10 THWN-2 conductors can you fit inside of a piece of 3/4-inch Schedule 80 PVC that already contains 3 number 12 THWN-2 conductors? We're going to head to Chapter 9, Table 4 and find our pipe. We're going to find the appropriate column based off the number of conductors, and we're going to find this value for a piece of 3/4. Then we're going to head to Chapter 9, Table 5 for our conductor properties, being sure to write down all the values that we need. First, we're going to take our number 12 that we already have, multiply it by the 3 that we already have, and that gives us this value. Then we're going to take our total available to fill, minus what we already have, and that gives us this for our remaining left to fill. Then we just take that and divide. We divide that out and we find that we can fit 5.88 conductors, and in this case it is 0.8 or larger, and we will round up to 6. Great job. What is the total area in square inches of a piece of 1-inch flexible metal conduit? For this one, we're going to head straight to Chapter 9, Table 4. When we get there, we're going to verify that we're in the right type of conduit. Then we're going to start on the left-hand side and find our size of conduit. Then we have to cross all the way over to the 100% fill area. I have been tested on this in the past, so it's good to be familiar with using this table on all spectrums. And in this case, we're going to select 0.817. Great job. Hey everyone, welcome back. I am the Electrical Code Coach from electricalexamcoach.com, and this is lesson 8.1 in our video series. We're going to be in Article 240, and we're going to be learning all about overcurrent protective devices. You'll hear me use the term OCPD throughout the rest of the program, and all it stands for is overcurrent protective devices. But to simplify it even further, just think about it like this. Anytime you see OCPD, it just means breakers and fuses. Whether it's the individual breaker at a branch circuit, 20 amp, or it's a 100 amp feeder breaker, or our main 200 amp disconnect. It's either going to be a breaker or fuse, and they're all OCPD. Let's get to it. Table 240.6a is one of my favorite tables in the NEC. It's where we get our standard ampere ratings from. And although it seems like the least of all the tables, it's very powerful throughout the electrical industry. Anytime we come to a new table, we always read the black bold heading to make sure that we're in the right table. Standard ampere ratings for breakers and fuses. Starting on the left-hand side is where it starts with our numbers. You should pull your codebook out and look at it now. If you're in the 2023 and later, it's going to start with 10 amps and go up. And in the 2020 and previous, it's going to start with 15 amps and go up. And then it goes up by fives: 15, 20, 25, 30, 35, 40, 45, 50. And when we get to 50, it starts jumping by tens and even larger numbers as we move up in amperage. The reason that this table is so important is it unifies the entire electrical industry. The manufacturers make these size breakers. The stores stock these size breakers. Installers purchase these size breakers, and when we are doing our load calculations in the NEC, these are the sizes that we're actually going to use. We're going to learn all about it in this lesson. Table 240.6a, standard ampere ratings for breakers and fuses. Let's get to it. Let's look at the major points for general overcurrent protective devices. I say general for a reason, because there are other parts of the code that modify, change, or erase the things that I'm getting ready to teach you. A good example is when we get to motor overload devices. But these rules that we're getting ready to learn apply blanket across the NEC unless another section tells you otherwise. The first one is the next size up rule. And that's the next standard size on that table that we just learned about. Let's imagine that we have a 59 amp known load. And for the rest of the program, I'm going to call it known load. And there's a reason that you'll learn about here in a minute. But do they make a 59 amp breaker? They don't, do they? What we would do is we would go to our table, 240.6a, and we're going to look at the next standard size. So we go 15, 20, 30, and then we look here and we see 50. And then in between 50, there's no 55, and it jumps to 60. If we have a 59 amp load, we're going to choose a 60 amp overcurrent protective device. Now, that may not feel good at first when you first start wiring and learning this stuff, but later we'll understand that there are rules in place when we get to sizing our wire that are going to make it so everything's okay and we're totally protected. The next major point is going to be continuous loads at 125%. There are two different names that you may see: continuous load or continuous duty. A continuous load is defined as expected to run for 3 or more hours at full current. And in the exam prep world, it's going to look like this. You have a load that's known to run for 5 hours. What would the blah, blah, blah? And it'll ask you for wire size or breaker size. Or it might say 5 hours or 10 hours. It doesn't matter how many hours it is. If it's 3 or more, it's considered a continuous load. You may also hear the word indefinitely. Just to try to throw you off, they might use the term indefinitely. Well, it falls under the same classification of needing a 125% multiplier. Remember, it's just another demand factor. Let's do an example. Let's take our 59 amp known load from before, and let's imagine that it was told to us that it's a 59 amp continuous load. What we would do is we would take our 59 amps, multiply it by 1.25, then we have a new known load of 73.75. That old load is gone. The 59 is gone. The 73.75 is our new known load. And that's what we would go size our breaker and subsequently our wire by. How we would do that is head to table 240.6a. We're going to look at the next standard size. So we're above 70 and it jumps to 80. And we would put this on an 80 amp overcurrent protective device. Our final major point is going to be that the overcurrent protective device equals the service size. Let me explain what I mean. Let's imagine that we did a whole house load calculation and it equaled 180 amps. Well, now we have to size the main breaker for that house, don't we? For that, we're going to head to table 240.6a and we're going to choose the next standard size. We put it on a 200 and we're done. But the question is what size is the service? Is it based off like the rating of the equipment bus? Maybe it's a 225 rated. No, it's actually based off the size of the main breaker or main fuse for that structure. So this would in fact be a 200 amp service. The load calculation dictated what size breaker we used, and the breaker size that we used dictated the size of the service. And this is very important as we get farther into the program. That's it for lesson 8.1. You can head over to electricalexamcoach.com to unlock the practice quizzes and everything in the ECC Testing Center. I am the Electrical Code Coach, and my bargain is that these videos will add value to you, and you will in turn add value to others. Let's get to it. Hey everyone, welcome back. I am the Electrical Code Coach from electricalexamcoach.com, and this is lesson 8.2 in our video series. And in this lesson, we're going to learn how to size overcurrent protective devices for non-continuous and continuous loads. Let's get to it. What size breaker would you use if you had a 56 amp load on a piece of equipment? Step 1, find the total connected load. The known load as of right now is 56 amps. Now we check for demand factors. In this case, it doesn't mention that it's a continuous load or it's running for any specific amount of time. It also doesn't call out a specific type of equipment, like a motor or air conditioner compressor, that might lead us to other sections of the code. Therefore, there are no demand factors. We head over to table 240.6a and we select the next size up. In this case, we have a 56 amp load, which would lead us to select a 60 amp overcurrent device. Great job. What size breaker would you use if you had a 34 amp load on a piece of equipment? Step 1, find the total connected load. The known load as of right now is 34 amps. But we gotta check for demand factors. There are no continuous loads, and there are also no specific pieces of equipment. So therefore, there are no demand factors. We're gonna head to our table 240.6a, and we're gonna choose the next size up, which in this case would be a 35 amp breaker. And that's where I want to take the time right now to point out that you should always go to the table and verify the size that you should choose. This is where you can let field experience burn you when you're in the testing center. Because if we're out in the field and we see a 34 amp load, we might put that on a 40 amp breaker. So you might see 34 amp load inside the testing center and automatically assume that the next size up is 40. But you have to go by the values in the table. The correct answer in the field and in the testing center in this case would be a 35 amp breaker. Let's get to it. What size breaker would you use if you had a 40 amp load on a piece of equipment? Step 1, find the total connected load. The known load right now is 40 amps, but we check for demand factors. And in this case, there are no continuous loads or specific piece of equipment. Therefore, there are no demand factors. We're going to head to table 240.6a. Even though we feel confident that it's a 40, I want you to always be in the practice of flipping to the table and verifying that you have the correct size breaker. And in this case, we land right on a standard size, so we're going to select 40. And we select D. Great job. What size breaker would you use if you had a 26 amp load in a house and it's known that it will run for 4 hours at a time at full current? Step 1, find the total connected load. Our known load as of right now is 26 amps. Now we got to check for demand factors. In this case, it's going to qualify as a continuous load. Any load that's expected to run for 3 or more hours at its full current must have that 125% continuous load multiplier. So we take our known load multiplied by 1.25. That gives us a new known load of 32.5. In that case, we would round up to 33, and that's our new known load. Then we head to table 240.6a, and we choose the next size up. And in this case, it's going to be a 35 amp breaker. Great job. What size breaker would you use if you had a 40 amp load in a house and it's known that it will run for more than 5 hours at a time? Step 1, find our total connected load. Our known load as of right now is 40 amps. But we must check for demand factors. And in this case, we have our continuous load multiplier. It's very important to note that the test makers will put different numbers of hours to see if you're paying attention. They'll put, what if the load runs for 16 hours or 20 hours? If it's anything 3 hours or more, it's going to have that 125%. We take our known load multiplied by 1.25, and that gives us a 50 amp new known load. We head to table 240.6a, and we're going to land directly on a standard size breaker, which is a 50. So we come back and select A. Let's get to it. What size breaker would you use if you had a 47 amp load and it was expected to run indefinitely? Step 1, find the total connected load. Our starting known load is 47 amps. Now we check for demand factors. And in this case, it gets that 125% continuous duty, just like a continuous load. We take our starting known load, multiplied by 1.25, and that equals 58.75. And in this case, we would round up. So 59 is our new known load. Now let's head to table 240.6a. And in this case, we're going to select the next size up, which happens to be a 60. Great job. That's the end of lesson 8.2. And I want to take this moment and encourage you and let you know that you're doing a great job and keep up the hard work. And just don't forget the reasons that you're doing this. For your family, for your career, for taking your family from where you guys were to where you guys are going. Because it's easy when we get exhausted and it's hard and we're on our way to that next level to forget all the reasons that we're doing this in the first place. I want to let you know that I'm here for you. Anything that you need, you can always just email me at electricalcodecoach@gmail.com. I am the Electrical Code Coach, and my bargain is that these videos will add value to you, and you will in turn add value to others. Let's get to it. Hey everyone, welcome back. I am the Electrical Code Coach from electricalexamcoach.com, and this is lesson 8.3 in our video series. We're still in Article 240, but we're going to be doing sample calculations of whole homes and businesses and selecting the main overcurrent device. Learning how to take all the work that we've done in the program up until this point, the load calculations and everything, and then take those total VAs and find out how to choose that overcurrent device, which will ultimately dictate the size of the service. Let's get to it. What size main breaker would you select for a home with a total calculated load of 23,123 VAs on a 120 240 volt system? Step 1, find our total connected load. Well, they've already done the load calculation for us, so all we have to do is take our total known VAs and divide it, and that's going to give us our load in amps. And in this case, it's 96.35. We would round down to 96. Now we check for demand factors. Because this load calculation was already performed, there are no more demand factors to do. They were done along the way, right? We would have performed our range demand factor, our dryer demand factor, and then now we have this total lump sum of 23,123. So all we have to do is divide by 240, and there are no demand factors. Now that we have our known load, we head to table 240.6a, and we choose the next size up. And in this case is going to be a 100. Great job. What size main breaker would you select for a home with a total calculated load of 47,000 VAs on a 120 240 volt system? Step 1, find our total connected load. In this case, they've done all the math for us, and 47,000 are our total VAs. All we have to do is divide that by the system voltage. And in this case, it equals 195.83, and we would round down. Now we check for demand factors. And in this case, there are no demand factors because they were already performed to get us that 47,000 value. Now we head to table 240.6a and choose our next standard size. And in this case, it ends up being a 200 amp breaker. Great job. What size main breaker would you select for a home with a total calculated load of 38,000 VAs on a 120 240 volt system? Step 1, find our total connected load. They've already done the math for us, so all we have to do is divide by the system voltage. And in this case, it equals 158. Now we check for demand factors. And like we said before, there are no more demand factors on this calculation. We head over to table 240.6a and we choose the next standard size breaker. And in this case, it's 175 amps. What size main breaker would you select for a business with a total calculated load of 95,000 VAs on a 140 240 volt system? Step 1, find our total connected load. They've already performed the load calculation for us, so all we have to do is divide by the system voltage. and we end up with 395.83, and we would round up to 396. Now we check for demand factors. And whether it's a home or a business, all the demand factors were already performed to get that original 95,000 number. So there are no more demand factors. Now we head to table 240.6a and we choose the next standard size breaker. And this would be a 400 amp breaker. This would also be a 400 amp service. Let's get to it. Now let's do that exact same calculation but on a three-phase system and show you the beauty of three-phase. What size main breaker would you select for a business with a total calculated load of 95,000 VAs on a 120/208 three-phase system? Step 1, find our total connected load. Well, they've already given us our total VAs, so all we have to do is divide. But with three-phase, there's one extra step. Because of the geometric nature of three-phase, we have to take that 208 and multiply it by the square root of 3. The square root of 3 just so happens to be 1.732. Once we work that math out, we end up with 360.256. And it seems like a lot of work on the front end, but you'll find out that you'll trade this little bit of math for what this is getting ready to provide for us. Now we can take and do our math, and after we divide it out, we end up with 263, and of course we would round up in this case. There are no more demand factors, so we head to table 240.6a and choose the next standard size. And this is where the beauty happens. We're going to now put this on a 300 amp breaker instead of, like in the previous question, it would be on a 400 amp, meaning that we'd have to have larger wire in the previous question, which may lead us to have larger pipe, which we may end up with a larger cost of overall project. The beauty of three-phase is the numbers come down. So this one's on a 300 amp service, which means we can put it on smaller wire, which might mean we can put it in smaller pipe, which might end up having a smaller overall cost. Let's get to it. What size main breaker would you select for a business with a total calculated load of 80,000 VAs on a 120/208 three-phase system? Step 1, find our total connected load. In this case, they've done the work for us. They've given us the 80,000. Now all we have to do is divide. We do our little bit of pre-work and we end up with 360. Now we take and divide that out and we end up with 222 amps. In this case, we'll round down to 222. There are no more demand factors in this calculation. We head over to table 240.6a, choose the next standard size up, and put this on a 225 amp service. That's the end of lesson 8.3. You can head over to electricalexamcoach.com. Let's get to it. Hey everyone, welcome back. I am the Electrical Code Coach from electricalexamcoach.com. And this is lesson 9.1 in our video series. We're going to be in Article 310, and we're going to be learning all about ampacity. Ampacity is the maximum current measured in amperes that a conductor can continuously carry under its usage conditions without exceeding its rated temperature. Everything that we're doing in this program and out in the electrical field is to protect first the people and then the equipment. And it's no different with the wire. This wire is only rated to handle so many amps before the insulation will start to deteriorate, and ultimately we could end up with a fault, short circuit, or just arcing and sparking. With that being said, in this video series, we're going to slow down and we're going to master wire ampacity and how many amps a wire can hold and how to select the right wire for the right load. Let's get to it. Now let's learn about our primary ampacity table. If you're in the 2017, it's table 310.15B16. And in the 2020 and later, it's table 310.16. Same information, new name. If you're in a softbound NEC, these should be your page numbers depending on what print of the NEC you have, whether you got the first round or second round print, but this will get you close enough. The most important thing is read the title of the table and make sure that it matches the actual table number. Let's get to it. Now there's a lot going on in this table. We're going to slow down in this lesson. This is our ampacity basics lesson, because if you don't get this, it's going to be hard to have an electrical career. It's going to be hard to ever be able to pass your examination. So we're not in any hurry. If you need to watch this video over and over, you can do it. The first distinction we want to make with this table is that it's actually two tables. On the left-hand side is going to be for copper conductors, and on the right-hand side is going to be for our aluminum and copper-clad conductors. Left-hand side copper, right-hand side aluminum, and if you'll notice, they mirror each other, but in the NEC, it's smushed all into one table. Now let's take a look at what all this information means. Now we're going to do a quick breakdown of the table. We won't stop on any specific part until we need it in the program because I don't want to confuse you. And later you'll understand why I did it piece by piece. But we read all of our tables from top to bottom, left to right. I want you to focus on the left-hand side because that's the copper side, but you'll notice that everything that we do is going to be mirrored over on the aluminum side. So starting at the top, it gives us the scope of the table. We're not going to get into that right now. It comes later in the series. Then you'll notice there's a 60, 75, and 90 degree C columns. Below that are going to be the insulation types like THHN, THWN. On the left-hand side, you're going to have the conductor sizes, which is easy. And then in the middle, you'll find the allowable ampacity for each respective column. Now let's take these piece by piece and explain exactly how to use them. Now let's learn about terminals and insulation rating. And that's where these 60, 75, and 90 degree C columns come into play. Whether we're dealing with terminals or insulation around the wire, each one of them can only handle so much heat safely. Whether it's a lug or a breaker or a switch or the insulation around the wire, they're all rated for specific temperatures. I'll give you a little heads up. Out in the field, all of these are almost 99% of the time rated for 75 degrees C. And the insulation has multiple ratings. Some of them are rated for 60, some of them are rated for 75, and some of them are rated for 90. The reason this is important is it's going to help us choose which one of these columns we select our ampacity from. If the terminals are rated 75 degrees, we're going to choose the 75 degree C column most of the time. I'll explain what most of the time means later in the program, because this section is just like other sections of the NEC. There are blanket rules that apply generally, but later they get modified. But for right now, what I want you to remember is we're going to match the column that we used based off the terminals that the device is rated by. Regardless of what the insulation is, we can choose from whatever column that the terminals are rated by, unless modified by another code. Now let's lay some ampacity ground rules. Unless modified by a specific piece of equipment or another code, these rules will apply generally. If the question states that it terminates to 60, 75, or 90 degree C terminal lugs, you're going to make your selection from that respective column. And as with overcurrent protection, we're going to do 125% demand factor for all loads that are expected to run for 3 or more hours. Remember our continuous load rule? That carries over into wire sizing as well. Let's get to it. What size AWG copper conductor would you select for a 60 amp load using THHW terminating on 75 degree C terminals? Step 1, find the total connected load. Well, in this case, we already have the load. It's 60 amps, but we must check for demand factors. They've not told us about a specific piece of equipment or that it's a continuous load, so there are no demand factors. But we have to learn one important rule for sizing wire. The wire must meet or exceed the known load. There is no next size up rule. The wire always has to meet or exceed the known load. So we head to our primary ampacity table, and we're going to start on the left-hand side because our question is copper. Always carefully go through these steps. What type of metal? Copper. What are my terminal ratings? They are 75 degrees C. What is my known load? 60. I'm going to start down the 75 degrees C column until I find a wire that covers the known load, and then I'm going to use a straight edge to come over and select my size wire. And in this case, you would put it on a 6-gauge wire. We go back and we select B. Great job. What size AWG copper conductor would you select for a 74 amp load using THHW terminating on 75 degrees C terminals? Step 1, find the total connected load. It's 74 amps. Now let's check for demand factors. Well, in this case, there's no specific pieces of equipment and there's no continuous load, so there are no demand factors. And we have to remember that our wire must meet or exceed the known load. We head to our primary ampacity table. We make sure that we're on the right side of the table. In this case, it's copper. And we have 75 degree C terminals. So now we take off and find a wire that will cover the known load. We find one that will cover 74 amps. We use a straight edge to come over and tee off at number 4. And we're going to select A. Great job. That's the end of lesson 9.1. You can head over to electricalexamcoach.com for quizzes that go along with these videos and unlimited access to the testing center. Ampacity is one of those topics that you have to take one bite at a time. So don't get overwhelmed. Take your time. I know that you can do it. I am the Electrical Code Coach, and my bargain is that these videos will add value to you, and you will in turn add value to others. Let's get to it. Hey everyone, welcome back. I am the Electrical Code Coach from electricalexamcoach.com, and this is lesson 9.2 in our video series. In this lesson, we're going to be sizing wire for continuous and non-continuous loads. Let's recap on the basics before we get started. If the question states that it terminates to 60, 75, or 90 degree C terminals, we're going to make our selection from that respective column under normal circumstances. And the second one is, as with overcurrent protection, like we learned before, we're going to do 125% demand factor for all loads that are expected to run for 3 or more hours. Let's get to it. What size copper conductor would you select for a 40 amp load using THHW terminating on 75 degree C terminals? Step 1, find the total connected load. In this case, we know the load, it's 40 amps, but we must check for demand factors. It doesn't mention a specific type of equipment or that it's going to be a continuous load, so in this case, there are no demand factors. And we always have to remember that all wire must meet or exceed the known load. So we have to find a wire that meets or exceeds 40 amps. We head to our primary ampacity table, and the first thing we're going to do is check the type of conductor. It's copper, so we're going to start on the left-hand side of the table. We're in the 75 degree C column because that's our terminal rating. Then we're going to slide down and find a wire that meets or exceeds the known load, and we find out that it's an 8-gauge conductor. And we select C. Great job. What size copper conductor would you select for a 60 amp load running for more than 5 hours using THHN type wire terminating on 75 degree C terminals? Step 1, find the total connected load. Well, our starting known load is going to be 60 amps, but we must check for demand factors. When we find out that it's going to be a continuous load, we need to remember to do our 125% rule for continuous loads. So we take our original known load, multiply it by 1.25, and that gives us a new known load of 75 amps to size our wire by. And remember, our wire must meet or exceed the known load. We head to our primary ampacity table. We head to the copper side because it wants copper conductors. We're in the 75 degree C column, and we need to go down and find a wire that meets or exceeds 75 amps, and we find that it happens to be a number 4. Let's get to it. What size copper conductors would you select for a 40 amp load that's considered a continuous load using THHN type wire terminating on 75 degree C terminals? Step 1, find the total connected load. In this case, our starting known load is 40 amps. Well, we have to check for demand factors, but they've already let us know that it's going to be considered a continuous load. We take our original known load, multiply it by 1.25, and that gives us a new known load of 50 amps. And all of our wire must meet or exceed the known load. We head over to our primary ampacity table. We're going to start on the left-hand side because they want copper conductors, and we're in the 75 degree C column. We come down and we find a wire that meets or exceeds our load, and we're going to put it on a number 8. Great job. What size aluminum conductors would you select for a 90 amp load running for more than 5 hours using THHN type wire terminating on 75 degree C terminals? Step 1, find the total connected load. Well, our starting known load is going to be 90 amps, but we must check for demand factors. In this case, we find out it's a continuous load. We're going to do our continuous load math. We take our starting known load multiplied by 1.25, and that's going to give us a new known load of 112.5 amps. Now, we have to remember that all of our wire must meet or exceed the known load. We head to our primary ampacity table, but this time we have to be careful because they are wanting aluminum conductors. So we're actually going to start on the right-hand side of this table. We're going to start on the right-hand side. We're in the 75 C column. We come down and we find a wire that meets or exceeds the known load, and we find out that it needs to be on a 1/0. Let's get to it. That's the end of lesson 9.2. You can head over to electricalexamcoach.com to get the quizzes that go along with these videos and unlimited access to our testing center. I am the electrical code coach, and I want you to know that you're doing a great job. If you need anything from me, you can always just email me at electricalcodecoach@gmail.com. Don't give up. I know you can do it. Keep grinding. Let's get to it. Hey everyone, welcome back. I am the electrical code coach from electricalexamcoach.com. And this is lesson 9.3 in our video series. In this lesson, we're going to be sizing the overcurrent protective device and the wire in the same question for all of these loads, for continuous and non-continuous. Let's recap very quickly. If the question states that it's terminating to 60, 75, or 90 C terminal lugs, you're going to make your selection from that respective column under normal circumstances. With both OCPD and wire sizing, we still have that 125% demand factor for all loads that are expected to run for 3 or more hours. And we will always select the overcurrent protective device first, and then we'll choose our wire size. And it'll make more sense why we do that once we start sizing services in the next lesson. And once we get into larger amperage questions like 1,000 amps or greater, which we'll learn in the lesson after that one. Let's get to it. What size copper conductors and overcurrent protection would you select for a 54 amp load using THHN type wire terminating to 75 C terminals? Step 1, we're going to find our total connected load. In this case, we have it. It's 54 amps. But we must check for demand factors. Well, they've not mentioned a specific piece of equipment or that it's going to run for 3 or more hours. So in this case, there are no demand factors. Now, what we're going to do is size our overcurrent protective device first. You always size that first. So we head to our overcurrent protective device table, which is 240.6A for a 54 amp load. We're going to go down and choose the next standard size up. In this case, it's going to be a 60. Now, let's head and size the wire. For that, we're going to head to our primary ampacity table. We're going to start on the left-hand side and make sure that we're on the copper side because our question asks for copper. And we're in the 75 C column in this case. We're going to slide down and find a wire that covers the known load of 54 amps. And we're going to select a 6-gauge wire on a 60 amp overcurrent device. Let's get to it. What size copper conductor and overcurrent protection would you select for a 62 amp load using THHN wire terminating to 75 C terminals? Step 1, find our total connected load. In this case, it starts at 62 amps, but we must check for demand factors. With there being no special pieces of equipment mentioned or the fact that it's running for 3 or more hours, in this case, there are no demand factors. Now, we go ahead and size our overcurrent protective device. We head to our table with a 62 amp known load, and we're going to choose the next size up, which puts it on a 70. Now we can size our wire. For that, we're going to head to our primary ampacity table. We're going to be sure to start on the copper side because it's asking for copper. We're in the 75 C column. We slide down and find a wire that can cover the known load. And we find out that we're going to have a 6-gauge wire on a 70 amp breaker. Let's get to it. What size copper conductors and overcurrent protection would you select for a 105 amp load using THHN type wire terminating to 75 C terminals? Step 1, we're going to find the total connected load. Our starting known load is 105 amps, but we must check for demand factors. It doesn't mention a specific type of equipment or for how many hours that it's running, so in this case, there are no demand factors. First thing we're going to do is size our overcurrent protective device. For that, we head to table 240.6A and choose the next standard size up. And this is why it's very important for you to always go to the table and not just go off of memory or what you might do out in the field. Because out in the field, you might say, oh, this needs to be on a 125 because 125 is a common number. But how many of you know that there's actually a 110 amp breaker in between 100 and 125? I've seen them, I've worked with them out in the field, but they're not very common. Usually out in the field, we'll jump from a 100 to a 125 for like sub panel sizing. But you have to be careful here. Always go to the table because the correct answer for this question is actually a 110 amp breaker. Now let's size the wire. For that, we head to our primary ampacity table. The known load's 105 amps. We're on the copper side of the table because that's what the question said. We're in the 75 degree C column, and we go down and find a wire that covers the known load, 105 amps, and we're going to end up with a number 2 wire on a 110 amp breaker. Great job. What size copper conductors and overcurrent protection would you select for a 105 amp load expected to run for 3 or more hours using THHN type wire terminating to 75 degree C terminals? Step 1, find the total connected load. 105 amps is our starting known load, but we must check for demand factors. When we look, we find that we have the 125% continuous load rule, so we do our math. We take our original starting known load, we multiply it by 1.25. That gives us a new known load of 131 amps. And now we can size our overcurrent protective device. We head to table 240.6a and we choose the next standard size, which is a 150. Now we can come back and size the wire. We head to our ampacity table. We're on the copper side, 75 degree C column. We're going to go down and we're going to find a wire that covers the known load. And we're good to go. We're going to select a 1/0 on 150. Let's get to it. What size copper conductors and overcurrent protection would you select for a 50 amp load expected to run for 3 or more hours using THHN type wire terminating to 75 degree C terminals? Step 1, we're going to find the total connected load. Our starting known load is 50 amps, but we must check for demand factors. We see that it's a continuous load, so we're going to have our 125% rule. We take our starting known load, multiply it by 1.25, and that gives us a new known load of 62.5. Now we can size our overcurrent protective device. We head to our table, we choose the next standard size, which in this case is going to be a 70. Now let's size our wire. Heading to our primary ampacity table, we're going to be on the copper side of the table in the 75 degree C column, and we find a wire that meets or exceeds the known load. When we do, we find that it needs to be a 6-gauge wire on a 70 amp breaker. Great job. This is end of lesson 9.3. You can head over to electricalexamcoach.com to check out our pro version. I am the Electrical Code Coach, and my bargain is that these videos will add value to you, and you will in turn go out and add value to others. Let's get to it. Hey everyone, welcome back. I am the Electrical Code Coach from electricalexamcoach.com. And this is lesson 9.4 in our video series. And in this lesson, we're going to be sizing the overcurrent protective devices and wire for commercial and dwelling unit services and feeders. We're actually going to start with commercial because it's easier, believe it or not. Always remember that we're going to select our overcurrent protective device first, and then choose our wire size. Also, the overcurrent protective device size is the size of the service. If we're sizing services and we select a 200 amp overcurrent protective device, whether it's a breaker or fuse, based off the size of the load, and we go to the next size up and it ends up being a 200, that means we have a 200 amp service. And it's very important for us to understand that before we move on in the program, that if I'm sizing services and I end up with a 200 amp overcurrent protective device, and that is the main breaker on that service, that is now a 200 amp service. Let's get to it. What size main breaker and copper conductors would you select for a business with a total calculated load of 80,000 VAs on a 120/208 three-phase system on 75 degree C terminals? Step 1, find our total connected load. In this case, they've already given us the 80,000 VAs, but we have to do that little bit of pre-work first on all of our three-phase calculations like we learned before. We take 1.732, we multiply it by our system voltage, which is 208, and that gives us that 360 value. Now we can divide just like normal. We take the 80,000 VAs, divide it by the 360, and that gives us a 222 amp known load by which we can size our breaker and our wire by. But first, we must check for demand factors. In this case, there are no demand factors, so we can size like normal. Let's size our overcurrent protective device first, based off of 222 amps. We head to table 240.6a and we choose the next standard size. And in this case, it's going to be a 225. Now we can size our wire. We head to our primary ampacity table. We're going to be on the copper side of the table in the 75° C column, and we need to go down and find a wire that covers 222 amps. And in this case, we're going to select a 4-aught. When we put it on a 4-aught wire, we're going to select D, and we're all done. That's why we chose to do commercial first, because it's going off of all the things that we previously built in these lessons with no additional rules. In a few moments, we're going to be on residential, and you'll find that there are a couple extra codes that we need to know about. Let's get to it. What size copper wire would you select for a service with a 125 amp main breaker and a total connected load of 118 amps on a commercial building with a 120/208 service on 75° C terminals? Step 1, we're going to find our total connected load. In this case, they give it to us. It's 118 amps, but we must check for demand factors. In this case, there are no demand factors, so we're going to carry on. Normally, we would size our overcurrent protective device, but if you notice in the question, they've already done that for us. So all we have to do is size our wire. We're going to head to our primary ampacity table and find a wire that is good for 118 amps. We go down, we slide down the 75° C column on the copper side, and we're going to find that we select a number 1. And in the testing center on the Electrical Exam Coach website, you'll have more variants of this and practice of this, but that's how easy it is with commercial. First, size the breaker based off the known load, and then you're going to size the wire. It really is that simple. Now let's dive into residential and learn a few more codes. Now let's learn how to size dwelling unit services and feeders in between 1 and 400 amps. This applies to single-family dwelling units and the individual units of two-family and multifamily dwelling units, and it's affectionately called the 83% rule. The next few slides are very dense, so I want you to slow down, take your time, watch it as many times as you need, but I know that you can do it. Keep up the great work. Let's imagine that we have a dwelling, and the first thing we're going to do is find our total connected load. Let's imagine that it's 47,000 VAs on a 240 volt system. That gives us 195.83. We would round up to 196 and go size our main breaker. And the main breaker would be a 200. That's the next standard size. We now have a 200 amp service. Now the next step normally would be to size the wire at 196 amps, right? That's our known load. We can just follow our normal ampacity rules. Well, not with services that are in between 1 and 400 amps. And let me show you what I mean. Let's all head to page 800 if you're in the 17, this table if you're in the 20, and this table if you're in the 2023. This is technically called the 83% rule, but I'm not going to force you to do the longhand math. I'm going to take you to these tables that are in the NEC that are almost like a cheat sheet that makes this super easy to apply and understand. Let's get to it. Once we get to our table, we work all of our tables from top to bottom, left to right, using those headings to navigate the table. On the left-hand side, we're going to find the size of the service and feeder, and this is listed in amps. And you'll notice that it only goes to 400 because the rules that we're learning right now only apply to services and feeders that feed the entire dwelling in between 1 and 400 amps. And I've got a great graphic illustration in the next slide to show you when it does and does not apply. On the next column over, we're going to see the copper side if we decide to use copper, and then aluminum if you decide to use an aluminum. So what you do is size your service. You come down here. Let's imagine it's a 100 amp service and you want to use copper. You slide over and it tells you what size wire to use. It makes it super simple. Now let's put it to practice. Now let's find out when this rule does and does not apply. Let's imagine that we have a single family dwelling. We have the meter socket outside, we have the riser, and we have a back-to-back panel, kind of an old school setup. We have the wire going up the riser and the wire going inside. Technically, this is all service wire all the way to that main breaker, and the 83% rule does apply here, as long as it's in between 1 and 400 amps. Now let's imagine that we have a main breaker outside, we have the service riser, and we have a main sub panel inside. We have the riser wire and the wire going inside. The 83% rule applies to all this wire. You can apply it to the wire going up the riser, and you can apply it from the meter disconnect combo to the first main sub panel. Now the rules with this is that it has to be the panel that feeds the entire structure. You're not allowed to use it on other sub panels or on any sub panel that does not feed the entire structure. You have to be very careful with that one. So we're allowed to apply it on this one on the left for the whole wire. We go use that table and size our wire based off the table. And the scenario on the right for all of that wire there for the service itself, and then also for the main feeder, as long as that panel that it's feeding is feeding the entire structure. You would go to that table, do your cheat sheet, find your size breaker, slide over, and you'd be able to use that size wire. Let's dive into two-family and multifamily. This is 1 through 400 amps, and this applies to the feeders only. The feeder must feed the entire dwelling. Let's imagine that you have an apartment here on the right-hand side, and it's attached to the larger apartment structure. That's where the main service is. Let's imagine that you have your meter center out here, you have your service riser, and then you have your wire going up. That wire there, the 83% rule does not apply. You're going to use all of the previous rules that we learned before and apply those. But the individual feeder going into that unit does. The 83% rule does apply. And the beauty of this is it allows you to save money in the long run. Whether you're doing single family dwellings only or you're doing the individual units of the apartments, you're going to be able to use a smaller wire based off that table than you would if you went and sized it like normal. And over a year's time, that could save you a lot of money. So that is when the 83% rule does and does not apply. What size copper wire and main breaker would you select for a service with a total calculated load of 47,000 VAs for a single family dwelling on a 120 240 volt system with 75 degree C terminals? Step 1, we're going to find our total connected load. In this case, they've given it to us, but we have to divide to get our amperage. When we do, now we can check for demand factors. And in this case, we do have a demand factor. Is this in between 1 and 400 amps? Yes. Is this on a single family dwelling? Yes. So the 83% rule does apply. So we get to use the table. Step 1, we're going to size our overcurrent protective device. And we're going to head to table 240.6a. We have a 196 amp known load. We're going to choose the next size up and put it on a 200. Now we can use our cheat sheet table. When we head there, we're going to size the wire. Step 1, we're going to be on the left-hand side and find our size breaker. Then we're going to come over to the copper column because that's what it requested, and we're going to find that we need to put it on a 2-aught. And in this case, we would have 2-aught copper on a 200 amp service. Great job. What size aluminum wire and main breaker would you select for a service with a total calculated load of 47,000 VAs for a single family dwelling on a 120 240 volt system with 75 degree C terminals? Step 1, we're going to find our total connected load. In this case, they've given it to us, and we're just going to divide, just like we did before. Now, we check for demand factors. Is this in between 1 and 400 amps? Yes. Is this on a single family dwelling or the individual unit of like an apartment? Yes. So, the 83% rule does apply. And we're going to go size our overcurrent protective device. We end up putting it on a 200 amp breaker, just like we did before. But now we have to be careful because the question is asking for aluminum. We head to our cheat sheet table. We start on the left-hand side, and we're going to find our size breaker. Then we have to slide all the way over to the aluminum column, and we're going to find out that it's a 4-aught aluminum. Great job. That's the end of lesson 9.4. When it comes to these type questions, the only way to beat it is through repetition. And the best way to do that is at electricalexamcoach.com. We teach you so much more inside of the quizzes that we don't get the chance to cover inside the videos. There are so many different nuances, different levels, and just topics that we haven't covered on video that we cover inside of those quizzes that are in the testing center at electricalexamcoach.com. I am the Electrical Code Coach, and my bargain is that these videos will add value to you, and you will in turn add value to others. Let's get to it. Hey everyone, welcome back. I am the Electrical Code Coach from electricalexamcoach.com, and this is lesson 9.5 in our video series. And in this lesson, we're going to be learning about bundling adjustments and ambient temperature corrections. These are a subset of ampacity. And remember, ampacity is just how many amps the wire can handle safely under its conditions of use without exceeding its temperature rating. Bundling adjustments work like this. When wires are bundled, like in a pipe for example, they have less ability to dissipate the heat, and it reduces how many amps the wire can handle safely. Ambient temperature corrections are like this. If wires are run in an extremely hot ambient temperature, it reduces how many amps the wire can handle safely. We're going to learn about these one at a time. Let's get to it. Let's dive into bundling adjustments. Let's take a look at our primary ampacity table. I want you to turn there now. And these values down below this table are true if, well, the question is if what? If you look at the paragraph above the table, the one that I said we would come back and look at later, it's got some parameters there. It says, hey, these are the ampacities of these conductors if, and the first if that we're going to look at is if there are not more than 3 current carrying conductors inside of a cable, pipe, or even buried in the earth together. Let's take a look at it. Let's imagine that we have a piece of conduit here and we pulled in a black, red, blue, and an equipment grounding conductors. What this table is saying is that those ampacity values listed down below in this table are true as long as you have not more than 3 current carrying conductors in a cable, pipe, or raceway. If you do have more than that, then we have to do what's called a bundling adjustment. Let's learn about our bundling adjustment table. Head to this respective table depending on your code cycle. When we get there, we're going to find that it's very easy to read. Reading all of our tables from top to bottom, left to right, we're going to start here on the left-hand side, and this is our number of current carrying conductors. Let's imagine we have this conduit, and we end up with 6 current carrying conductors. So we're going to slide down until we find our range, and we fall in the 4 to 6 range. Then we need to slide over and find our adjustment factor, which is just another demand factor, which is something you're very familiar with at this point in the program. Let's imagine we have a wire that's 50 amps. We take that 50 amp wire and we multiply it by 0.80, which was our demand factor. And we end up with a wire that is now only good for 40 amps. What they're saying is because the amount of wires inside of this pipe or cable that the wire cannot dissipate the heat safely. So you have to reduce how many amps the wire can handle. So the new allowable ampacity of this wire is only 40 amps. Up until this point, we've had all hot conductors inside of our conduit. But what happens if we add in a neutral? Is it considered a current carrying conductor? What about grounding conductors? Are they considered current carrying conductors? Well, let's learn how to count conductors now. Now let's learn about current carrying conductor counting, because we're only going to be counting the current carrying conductors. You may get a question on your exam that gives you the number of conductors. That's easy. You're going to go to the tables and do the math. But you may get a question on your exam that asks you in a scenario of wires, how many of them are current carrying conductors? The first one's easy. All ungrounded conductors. All of the hots are going to be considered current carrying conductors under normal circumstances. The second one is the neutral of a line to neutral load, meaning if we have a light bulb and it draws 1 amp on a 120 volt circuit, there's going to be 1 amp going in on the hot and there's going to be 1 amp flowing back on the neutral. So it is as well a current carrying conductor. Same thing with a 3-phase 4-wire neutral. We're not going to be dinking around trying to calculate the unbalanced load. We're just going to count it as a current carrying conductor. Then the 3-phase nonlinear neutral load. Nonlinear loads come from large fluorescent lighting or from large computer data centers, you're going to count its neutral as well. Grounding conductors, no, they do not count, and that's one of the easiest ones. You don't have to count those as a current carrying conductor. If we have no adjustment will be made if we have nipples that are 24 inches or less. Let's imagine we have a panel over here on the right-hand side. We put a panel on the left side. We want to run a short nipple that's 24 inches or less. This does not count in our bundling adjustment. Now let's talk about choosing from the right column. And this is the last step before we're actually able to start doing questions. Up until this point, we've always chosen, most of the time, from the 75-degree C column. Now, there'll be times that we choose from the 60, and this is where we start choosing from the 90. 99% of the time, you're going to choose from the 90 anytime that you're doing bundling adjustments or temperature corrections. We're going to choose from that 90-degree C column. We're getting ready to do practice questions, and you'll understand that more fully as we proceed. What is the allowable ampacity of a number 4 copper conductor with 9 current carrying conductors in a piece of 1-inch EMT? Step 1, we're going to verify that our conductors are listed in the 90-degree C column. We head to our primary ampacity table on the copper side, and we make sure that THHN is listed. If it's not listed there, for the purpose of exam prep, I just want you to go to whatever column that it is listed in and do the math. Now, we're going to find our starting ampacity in the 90-degree C column. We head to our primary ampacity table. It's wanting a number 4 conductor, so we start on the left-hand side. We're going to come over and we're going to tee off with the 90-degree C column, and we're going to find out that it is 95 amps. That's our starting ampacity. Now, we must check for demand factors. Are there more than 3 current carrying conductors? There are, so we must apply the demand factor. We're going to head to either table depending on what code cycle you're in. It is our bundling adjustment factor table. And when we get there, we're going to start on the left-hand side. We come down and find our number of current carrying conductors. Then we cross over and find our demand factor. Now we can get to work. We take our starting ampacity, we multiply it by the demand factor, and that gives us a new allowable ampacity of 66.5 amps. A wire that was once good for 95 amps, because of it being bundled in this pipe, is now only good for 66.5, and we select A. Great job! What is the allowable ampacity of a 1-aught XHHW copper conductor with 13 current carrying conductors in a piece of 2-inch RMC? Step 1, we're going to verify that our conductors are listed in the 90-degree C column. When we head there, we find that XHHW is listed. So we're going to find our starting ampacity. We head to our primary ampacity table. We're on the copper side. We start until we find 1-aught on the left. Then we cross all the way over to the 90, and we find that it's 170 amps. Now we check for demand factors. Are there more than 3 current carrying conductors? There are. So we must apply the adjustment factors that are listed in these tables. We go to our adjustment factor table. We're going to start on the left-hand side and find our number of current carrying conductors. Then we cross over and find that it's 50%. We take that and do our math. We take our starting ampacity multiplied by the bundling adjustment factor. Then we're going to have a new reduced ampacity of 85 amps. Great job! What is the allowable ampacity of a number 6 THHN aluminum conductor with 6 current carrying conductors in a piece of 3/4-inch EMT? Step 1, we're going to verify that our conductors are listed in the 90-degree C column. We head there now, but we're on the aluminum side because the question requested aluminum conductors, and we find that THHN is there. Now we find our starting ampacity in the 90-degree C column. We head to our primary ampacity table on the aluminum side, and we slide down until we find a number 6. Then we're going to come over and we're going to cross over and find that our starting ampacity is 55 amps. But we must check for demand factors. Are there more than 3 current carrying conductors? There sure are. So we're going to head to our bundling adjustment factor table. When we get there, we're going to find our range of conductors. Then we're going to cross over to the demand factor. Now let's just do the math. We take our starting ampacity, multiplied by 0.80, and that gives us a new reduced allowable ampacity of 44 amps. Let's get to it. That's the end of lesson 9.5. I want to let you know that you're doing a great job. Keep up the good work. Keep grinding. If you need anything from me, whether it's mentoring, coaching, or any way that I can help you in life or business, you can always just email me at electricalcodecoach@gmail.com or shoot me a call or a text at 423-895-3247. If you don't get me, leave a voicemail and shoot a text. I am the Electrical Code Coach, and my bargain is that these videos will add value to you, and you will in turn add value to others. Let's get to it. Hey everyone, welcome back. I am the Electrical Code Coach from electricalexamcoach.com, and this is lesson 9.6 in our video series. In our previous lesson, we learned all about bundling adjustments and how to derate them when wires are bundled inside of a pipe, cable, or raceway. In this lesson, we're going to be learning about ambient temperature corrections. It's very similar. We just pull from a different table, but it's the same style demand factor process that we've been doing this entire program. Ambient temperature corrections are like this. If wires are run in an extremely hot ambient temperature, it reduces how many amps the wire can handle safely. And let's not forget the basic definition of ampacity. It's how many amps the wire can handle safely under its conditions of use. Let's get to it. Let's take another look at our primary ampacity table. In the last lesson, we learned about the first part of the note that's at the top of the table. And it says that these values are true as long as you don't have more than 3 current carrying conductors. But there's a second piece to this. Now, if you're in the 2017, it's at the top of the table. If you're in the 2020 and the 2023, it's at the bottom of the table. And what it's stating is that these values are true in this table as long as you're in an ambient temperature of 86 degrees Fahrenheit. Anytime you get outside of that ambient temperature, you're going to have to do an ambient temperature correction. Let's imagine that we have this circuit here, black, red, blue, and an equipment grounding conductor. Well, we know from the previous lesson that we will not have to do a bundling adjustment on this one because there's not more than 3 current carrying conductors. But what if we were in a factory who was making a plastic process and they had to have that room at exactly 115 degrees all the time for all of the machines to function properly? That's what we're going to learn about in this lesson when you run into those scenarios and you're pulling circuit conductors. Now let's learn about our temperature corrections table. Go ahead and head to your code cycles table number now. Pause the video if you need to. When we get to the table, we want to verify we're in the right table. And how we do that is make sure that we're in the table that says 86 degrees Fahrenheit. We do not want to be in the table that says 104 degrees Fahrenheit. The table looks identical, but it'll have all the wrong numbers that you need. So you want to make sure that you're in the table that says 86 degrees Fahrenheit. Then if you're able to in your state, I want you to highlight that table. Just highlight the title of it. So when you're flipping through and doing these questions, you're going to know that you're in the right table and you don't have to second guess yourself. Once we know that we're in the right table, let's break down the table. On the left-hand side, we're going to find our column in Celsius. And that's if your actual ambient temperature is in degrees Celsius. You would start on the left-hand side, find the degrees in Celsius, and then finish the process that we're getting ready to learn. Across the top, you'll see a 60, 75, and 90 degree C column. And those correspond with the 60, 75, and 90 degree C columns of our starting ampacity table. Then on the right-hand side, you'll notice degrees Fahrenheit. And that's if your ambient temperature is listed in degrees Fahrenheit. Let me give you an example. Let's imagine that we have this circuit here with our black, red, blue in it. And we have our equipment grounding conductor. Then let's imagine we're in an ambient temperature of 115 degrees Fahrenheit. We would start on the right-hand side and we would find 115 degrees. Then we would come over to the 90 degree C column and we would find our correction factor. And all it is another demand factor. And let's imagine that we had a wire that was 50 amps before we started. We found out that it was installed in an ambient temperature of 115 degrees. And we found out that our correction factor was 0.82. All we would have to do is take our starting ampacity, multiply it by 0.82, and we would end up with a new allowable ampacity of 41 amps. Great job! Let's talk about choosing from the right column. Just like with bundling adjustments, 99.9% of the time, we're going to be choosing from the 90-degree C column for our starting ampacity. And then we have to make sure that we choose from the 90-degree C column in our temperature corrections factor table. In the event of it not being listed there, we're likely going to choose from the 75 if it's listed there, but we have to make sure that we choose from the 75 over here as well. But that would be under very rare circumstances when you are in the testing center. But I just want you to know about it just in case. And one thing that I do want to mention at this point in the program is NM cable. NM cable is Romex, and it is actually allowed to be chosen from the 90-degree C column. Romex is just a trade name. They also have Southwire and other trade names. But in the code book, it's called NM cable. And for the purpose of bundling adjustments and temperature corrections, you're allowed to choose from the 90-degree C column when doing those calculations. What is the allowable ampacity of a THHW number 6 copper conductor with an ambient temperature of 142 degrees terminating to 75 degree C terminals? Step 1, we're going to verify that our conductors are listed in the 90-degree C column. We head there and look for THHW, and sure enough, it's right there. Now we're going to find our starting ampacity in the 90-degree C column. We head back to that table. We're going to start over here and find our number 6. Then we're going to cross over and find its ampacity in the 90-degree C. And in this case, it's 75. We're going to take our number 6 at 75. Now we're going to check for demand factors. Is the ambient temperature greater than 86 degrees Fahrenheit? It is, so there will be a demand factor. We're going to head to our respective table depending on our code cycle. And we're going to go find our correction factor. When we get there, we're going to start on the right-hand side because the question stated it in Fahrenheit. Then we're going to go down until we find our range of temperature. Ours was 142 degrees. Then we're going to slide over and find our correction factor. And remember, it's just a demand factor. Now, what we're going to do is we're going to head back and do our math. We take our starting ampacity multiplied by the correction factor, and that gives us a new allowable ampacity of 48.75, and we select B. Great job! What is the allowable ampacity of a number 10 THWN-2 copper conductor that is installed in an area with an ambient temperature of 145 degrees Fahrenheit? Step 1, we're going to verify that our conductors are listed in the 90-degree C column. We head to the table, we look for THWN-2, and sure enough, they're there. Now let's find our starting ampacity in the 90-degree C column. We head back to the table, we come down and find our number 10 on the left, and we cross over to 40 amps. Now we check for demand factors. Is the ambient temperature greater than 86 degrees Fahrenheit? It sure is. We're going to head to our table and find our correction factor. We're going to start on the right-hand side because it's Fahrenheit. We come down and find our range of temperature, which is 145, and we slide over and find our correction factor is 0.65. Now we go back and we take our starting ampacity multiplied by 0.65, and that gives us a new allowable ampacity of 26 amps, and we select D. What is the allowable ampacity of a 2-aught XHHW copper conductor that's installed in an area with an ambient temperature of 68 degrees Celsius? Step 1, we're going to verify that our conductors are listed in the 90-degree C column. When we head to the table, sure enough, they're there. Now let's find our starting ampacity. We're going to go to the table, start on the left-hand side. We're going to find 2-aught copper, then we're going to cross over and find 195 amps. Now we check for demand factors. Is the ambient temperature greater than 30 degrees Celsius? It sure is. So we know that there will be a demand factor. We head to our correction factor table, and in this time we're going to start on the left-hand side because it was listed in degrees Celsius. But we have to be careful to cross all the way back over to the 90 because that's the column that we chose from. And we find that our correction factor is 0.58. We take our starting ampacity, multiply it by the correction factor, and that gives us our new allowable ampacity of 113.1 amps, and we select A. Let's get to it. That's the end of lesson 9.6. You can head over to electricalexamcoach.com for practice questions and different variants of these type of questions. I am the electrical code coach, and my bargain is that these videos will add value to you, and you will in turn add value to others. Let's get to it.
Now we're going to learn about sizing motor conductors. 430 is one of the largest articles in the code book, so I'm only going to show you what you're going to be testing on. When sizing normal motor conductors, you will use the motor FLC and not the FLA nameplate. FLC stands for full load current, and that's a value that we find inside the code book. The FLA nameplate rating is typically the amperage value that they've stamped on the motor's nameplate. Remember how we've learned previously that every piece of equipment has a nameplate, and it'll say things like what voltage the equipment is and what the amperage is. Well, on motors, they'll typically stamp an amperage, but that's the FLA. So when we're sizing normal motor conductors, we're actually going to use the FLC, and I'm getting ready to teach you how to find that value. We're going to find these values in table 430.248, and that's for single phase. It's on page 321 of the 2017 or page 332 of the 2020. I want you to head there now, pause the video if you need to, and we're getting ready to go over this table. I'll give you a little hint. If you are able to tab your code book, there is a motor FLC tab that will take you right there. So the first thing that we do when we get to this table is we read the black bold heading. It says full load current in amperes for single phase alternating current motors. Great, I feel like we're in the right table. I would go ahead and take a moment, and if you can, and highlight that right there where it says full load current, and then highlight the word single phase. Okay? Highlight the word full load current and single phase. Now continuing to read the table from top to bottom, left to right, using the black bold headings to navigate the table, we're going to start on the left-hand side. And if you notice there, you have your horsepower. That's going to be whatever the horsepower of the motor is. Now across the top, all of those black bold headings are respective voltages. Okay? So what you do is you go to your horsepower, and then you come over and you tee off with whatever voltage your motor or your question states. Okay? So, and one thing I want to know is that these are nominal voltages. So although it says 115 at the top, it would also include 120. Although all the way at the end, it says 230 volts across the top of the black bold headings, you could still count 240 in that. These are nominal voltages. Another tip I want to give you is that even if the motor is a single phase motor, but your question states 208 volts, you use whatever column your question states. Don't try to use reasoning and say, well, 208 is only three phase. Whatever your question states, just do it that way. Now let's all head to table 430.250. That's for our three-phase motors. It's on page 322 of the 2017 and on page 333 of the 2020. And when we get there, it's going to be very similar. We always read the black bold heading. It says full load current for three-phase motors. I want you to highlight full load current and three-phase motors if you're allowed to highlight in your state. When we go to read this table, we're going to read it just the same. We start on the left-hand side. It's going to be our respective horsepower. And then coming across the top are our voltages. Again, I want to warn you, make sure that whatever the question states, you choose from that voltage. So even if it doesn't make sense, if they put 230 volts on a three-phase system, just do whatever the question states, okay? Don't try to change the reasoning there because it's very easy to do. So if the question stated a 7.5 horsepower motor on three-phase with 230 volts, you would go over and select an FLC of 22 amps, okay? And if it said a 7.5 horsepower motor for 208 volts, you would go over and tee off and find out that it has an FLC of 24.2 amps. Okay, now let's learn about some more ground rules for motors. You're going to multiply the FLC by 125%, okay? They consider motors continuous duty. Remember how we learned about continuous load and continuous duty previously? Well, it's the same thing. They're assuming that all motors are continuous duty, except, remember this is the National Exception Code, okay? Except when you're dealing with these certain circumstances, okay? For conductors on motors that are under 1200 RPM, that are intermittent duty, multi-speed, or high torque, you're actually going to use the nameplate FLA current rating. And for each one of these, there's going to be individual rules that apply. I'm only going to teach you in our lesson the ones that you're probably going to be tested on. Okay? So, and I'm going to say this over and over in every slide so you don't have to worry about remembering that right now. If it's a normal motor conductor, you're going to multiply the FLC by 125%. If it's any one of these other motors, under 1200 RPM, intermittent duty, multi-speed, or high torque, and your question will say that in there. And I'm going to teach you how to watch for these red flags. You're actually going to use the FLA rating. Why the code book doesn't stick with FLC or FLA only, I don't know, and I wish they would simplify it. Also, one thing I want to note for motor conductors. Remember in the ampacity lesson, we learned that 14 gauge wire can only go on a 15 amp breaker, 12 gauge wire can only go on a 20 amp breaker, and 10 gauge wire can only go on a 30 amp breaker? Well, with motors, these limitations do not apply. Those rules do not apply. So, now that we've set the ground rules, let's get to it. What size copper conductors would you select for a 3 horsepower, 208 volt, 3-phase motor that has an FLA nameplate rating of 9 amps terminating to 75 degree C terminals? One thing I want to note is that they're always going to put that FLA nameplate in there, rating in there to throw you off. So remember, when sizing normal motor conductors, you will use the FLC. For conductors on motors that are under 1200 RPM, intermittent duty, multi-speed, or high torque, you're going to use the nameplate FLA rating. For normal single motor conductors, you're going to multiply that FLC by 125%. So first we go find our FLC. We go to table 430.248 for single phase, and we go to 430.250 for 3-phase. Okay, so when we get to the table, we start on the left-hand side. So we look back at our question. What does it say? It says 3 horsepower. And then it also says 208 volts. So we start at 3 horsepower, we come over and we tee off with 208 volts, and we're going to find that that motor has an FLC of 10.6 amps. Now what we're going to do is take that 10.6 amps, we're going to multiply it by the 125%, 1.25. That's going to give us a new amp draw that we're going to size our wire by of 13.25 amps. Now we head to our primary ampacity table, being sure to select from the 75 degree C column because our terminals are 75 degrees. We're also selecting from a copper conductor. So we start, we go down, and we go on the 75 degree C side of the copper conductors until we find a conductor large enough to cover the known amp load. And in this case, it's 13.25 amps. And we're going to select A, 14 gauge. Great job. What size copper conductors would you select for a 5 horsepower, 208 volt, 3-phase motor that has an FLA nameplate rating of 15.2 amps terminating to 75 degree C terminals? Remember, when sizing normal motor conductors, you will use the FLC. On these types of motors, you're always going to use the FLA. Also, for normal single motor conductors, you're going to multiply that FLC by 125%. First, we need to find our FLC. We're going to head to our respective table. In this case, it's 3-phase, so we're going to go to 430.250. And when we get to 430.250, starting on the left-hand side, we're going to come down and we're going to tee off with our voltage, which is 208 volts, and we're going to find that the motor FLC for this motor is 16.7 amps. Now we take that 16.7 amps, we multiply it by 1.25. That's going to give us a new amperage of 20.875 amps, okay, and we're going to round up to 21. Now we head to our primary ampacity table in the 75 degree C column. We're going to start and we're going to go on the copper side, 75 degree C, and we're going to find a wire that is large enough to cover our known amp load of 21 amps. And we're going to select B. What size copper conductors would you select for a 7.5 horsepower, 208 volt, 3-phase motor that has an FLA nameplate rating of 28.6 amps terminating to 60 degree C terminals? Remember, when sizing normal motor conductors, you're going to use the FLC. If you have one of these specific situations, you're going to use the nameplate FLA. Also, for single motors, we're going to multiply it by the 125%. So we head to our respective table. In this case, it's 3-phase. So we're going to head to 430.250. Starting on the left-hand side, we're going to select our respective horsepower. Then we're going to come down and we're going to tee off with our voltage. Now we're going to select our FLC of 24.2 amps. Now we take that 24.2 amps, we multiply it by 1.25. That's going to give us a new amperage to size our wire by of 30.25. Now we head to our primary ampacity table, being very careful to select from the 60 degree C the 60 degree C column, because our terminals are rated 60 degrees C. And we're going to select C. Great job. What size copper conductors would you select for a 10 horsepower, 115 volt, single phase motor that has an FLA nameplate rating of 95 amps terminating to 75 degrees C terminals? Remember, when sizing normal motor conductors, you're going to use the FLC. When you have these motor situations, you're going to use the nameplate FLA. Also, for normal single motors, you're going to multiply the FLC by 125%. First, we're going to find our FLC. This case, it's single phase, so we're going to go to 430.248. Starting on the left-hand side, we're going to find our respective horsepower. Then we're going to come and tee off with our respective voltage. We're going to find that our FLC is 100 amps. Now we're going to take that 100 amps and we're going to multiply it by 125%. That's going to give us 125 amps. Now we head to our primary ampacity table in the 75 degree C column. In the copper side, we're going to go down and we're going to select a wire that will cover our known amp draw, in this case 125 amps. And we're going to select D. Great job. What size copper conductors would you select for a 10 horsepower, 230 volt single phase motor that has an FLA nameplate rating of 47.5 amps terminating to 75 degree C terminals? Remember, when sizing normal motor conductors, you're going to use the FLC. In these special conditions, you're going to use the nameplate FLA. Also, for normal single motor conductors, you're going to multiply that FLC by 125%. So first we go to our single phase table of 430.248. Starting on the left-hand side, we're going to choose our respective horsepower. Then we're going to come over and tee off with our voltage. Our FLC is 50 amps. Now we take that FLC, multiply it by 125%. That's going to give us 62.5 amps. Now we head to our primary ampacity table in the 75 degree C column. And we're going to select a 6-gauge wire. Great job. What size copper conductors would you select for a 10 horsepower, 230 volt single phase motor that has an FLA nameplate rating of 47.5 amps terminating to 60 degree C terminals? Remember, when sizing normal motor conductors, we're going to use the FLC. For these motors, we're going to use the FLA. Also, we're going to do that 125% rule. In this case, we're dealing with single phase, so we're going to go to 430.248. Starting on the left-hand side of the table, we're going to come down and find our respective horsepower. Then we're going to come across the top to our respective voltage and tee off. We're going to find that our FLC is 50 amps. Now we're going to take that 50 amps, we're going to multiply it by 1.25. That's going to give us a new amp draw of 62.5 amps to size our wire by. Now we're going to head to our ampacity table, being sure to select from the 60 degree C column. In the copper side, in the 60 degree C column, we go down and we find a wire that will cover our known amp draw. And in this case, we're going to select a number 4. Great job. What size aluminum conductors would you select for a 10 horsepower, 115 volt single phase motor that has an FLA nameplate rating of 95 amps terminating to 75 degree C terminals? We're going to use the motor FLC for normal motor conductors. Also, with these motors, we're going to use the FLA. For single motors, we're going to multiply the FLC by 125%. First, we find our FLC. In this case, it's single phase, so we go to 430.248. In that table, we find that we have an FLC of 100 amps. We take 100 multiplied by 1.25. That is going to give us 125 amps. Now we head to our primary ampacity table in the 75 degree C column, being sure to be on the aluminum side of the table. So we go down on the aluminum side and we find a conductor that will cover our known amp load. And we're going to select C. What size copper conductors would you select for 5 motors with FLCs of 24 amps, 13 amps, 13 amps, 10 amps, 9 amps, terminating to 60 degree C terminals? Now this one can look like a bear at face value, but once I explain it, it's not very complicated. Everyone head to 430.24. It's on page 303 of the 2017 and on page 314 of the 2020. We're going to go there and do some strategic highlighting. Pause the video now if you need to. Okay, so when we get to 430.24, we're going to read the black bold heading. It says several motors, okay? So what we're dealing with is when we have more than one motor. I want you to highlight, first off, I want you to highlight in the black bold heading, just highlight the word several motors if you're allowed to highlight in your state, okay? Then go down to part 1 and highlight 125%. And then go down to part 2 and highlight some, and just highlight all of part 2. Okay? So you're going to highlight the word 125% in part 1, and you're going to highlight all of part 2. So what this is stating, to simplify it for you, when you're dealing with multiple motors, you take the highest motor, so the highest FLC of all of them, and you multiply that FLC by 125%. Then you just add up all the other motors together and then total them back to the first one that you did the 125% on, and you take that number and go size your wire. Let's practice it on the next slide. All right, so the first thing that we do is we have to select our largest motor. And in this case, it's the 24 amp motor. So we take the largest motor and we multiply it by 125%. That gives us 30 amps. Now all we have to do is total the sum of all the other motors and then add it back to the first motor. So we take the rest of the motors and get that total. And in this case, it's 45. Now here's where we have to be careful to add back that first motor. So we take the 45 of the sum of the other motors, add back the first motor, and that's going to give us 75 amps. Now all we have to do is head to our primary ampacity table, being sure to use the 60° C column. Our conductors that they're asking for are copper. So we go down, what wire's good for 75 amps in the 60° C column? That's right, we're going to select D. Great job. What size copper conductors would you select for 4 motors with FLCs of 22 amps, 20 amps, 14 amps, and 10 amps terminating to 75° C terminals? So the first thing we're going to do is take our largest motor and do the 125%. We take our largest motor, multiply it by 125%, and that gives us 27.5 amps. Now we take all the other motors and add them together. That gives us a total of 44. Now we take and add those two totals together, giving us a total of 71.5 amps. Now we head to our primary ampacity table, and we're going to select on the copper side in the 75° C column a wire that is large enough to cover our known load. And in this case, we're going to select A. Great job. What size copper conductors would you select for a single phase motor with a nameplate rating of 26 amps that will run a drawbridge for only 5 minutes at a time, terminating to 60° C lugs? So this is not a normal situation, is it? So that's what you learn to watch out for when sizing motor conductors. Is there anything different going on? And in this case, there is. So we're going to slow down and figure it out. Everyone head to 430.22E. It's on page 302 of the 2017 and on page 313 of the 2020. There are provisions in the code book for when motors will only run for fixed or limited amount of times that you can have a reduced amp draw to size your wire by. Or sometimes it's actually an increased amp draw. So it's just really another demand factor. So everybody head there now. Pause the video now if you need to. So when we get to 430.22E, we're going to read the black bold heading. It says for other than continuous duty motors. Remember, all of our other motors, we did the 1.25 because it was a continuous duty. But what if they're not continuous duty? And that's what we're going to cover here. It lets us know that conductors for motors that are used short time, intermittent, periodic, or varying duty shall have an ampacity of not less than the percentages that are listed, okay, in 430.22E. Okay, so these ones we are going to go to 430.22E, and it's a table. It's usually on the next page of your code book. So whether you're in the 2017 or the 2020, it's typically in the next page over. When we get to table 430.22E, let's look at it now, starting with the black bold heading. It says duty cycle service. Pretty sweet. Now using our black bold headings, top to bottom, left to right. Starting on the left-hand side is going to be our classification of service. Okay, so on the left-hand side, we're going to pick whatever scenario our question lists. And if you look down through there, somewhere you're going to find something about a drawbridge, okay, or whatever your question states. Then going across the top in the black bold headings, you're going to see 5-minute, 15-minute, 30 to 6-minute, or continuous duty rated. So with that being said, what you're going to do is start on the left-hand side and find your situation, then come across the top and tee off with your amount of time. So what you will do is, when you get that value, it's just going to be another multiplier. It's just another demand factor. So let's look at the first one. In a 5-minute rated motor for short time duty operating valves. That's the first one you come to on the left-hand side. If you go over to a 5-minute motor, it's 110%. So all you do is take and multiply it by 1.10. It's just another demand factor. All right, so let's look at our question again and answer it. So in this case, we have a 26 amp draw. Remember, we don't use the FLCs on this type of question. You're going to use the nameplate rating. And we're going to have a drawbridge for 5 minutes. So we go to our table, 430.22e, starting on the left-hand side, and let's find something until it says the word drawbridge. Looking down, and if you look right there, in the middle section, it says drawbridges. Now we need to come over and tee off with our respective time. In this case, it's 5 minutes. So we find what type our motor is, then we slide over to our time limit, and we're going to find our multiplier, and we're going to take our amperage and multiply it by that demand factor. In this case, it's 85%. So we take our nameplate rating, multiplied it by 0.85, and that's going to give us 22.1 amps. Now we can head to our ampacity table and size a wire that can hold 22.1 amps, being sure to select from the 60° C column. So when we get there, we come on the copper side, 60° C, and let's find a wire that can cover our known load. And in this case, we're going to select C. Great job. What size copper conductors would you select for a 3-phase motor with a nameplate rating of 40 amps running some short time duty operating valves that will only run for 15-minute intervals terminating to 75° C lugs? One thing I want to note is that if you watched our video back in week 1 that teaches you how to make your own tabs, you should have made a tab for this table, okay? This is one of the tabs that we highly recommend making that are not in the Mike Holt tabs that we sell. So with that being said, you can use your tab for even faster reference to this table. So we see that there's something going on here, and we recognize that it's a duty cycle question. We're going to head to our demand factor table for duty cycles. It's 430.22e. Then starting on the left-hand side, we're going to look for our situation. In this case, it's short time duty operating valves. So when we find it, we come over and we tee off with our time, which is 15 minutes, and we're going to find a demand factor of 120%. Then we take our original 40 amps, multiply it by 1.20. Now we have 48 amps. Let's head to our ampacity table. Let's find a wire that will hold 48 amps in the 75° C of the copper side. And in this case, we're going to select D. Great job. Now we're going to learn about motor short circuit ground fault protection. There are 2 types of protection for a motor. One of them is called short circuit ground fault protection, and the other one is called overload protection. They are 2 separate things, and they've named them on purpose so you would know what rules to apply. So let's learn about what they both are, and that way we can rightly divide them. And all I want you to think about, so you don't overcomplicate it, is both of these protections are just breakers and fuses. Okay? And that is was so hard for me to understand at the beginning, is that because you hear these 2 different types of protection and you can really get lost in the sauce, but all they are breakers and fuses. And I'm going to explain how a basic short circuit ground fault protection and motor overload setup would work now. Okay, so we have both the types of protection. Let's imagine that this is a motor. Next to the motor, there's a disconnect. And then feeding that disconnect, there's a panel. Okay, at the original panel is where you're going to put your short circuit ground fault protection. At the disconnect is where you're going to put your motor overload protection. The first protection, the short circuit ground fault protection, what do you think it protects against? That's right, short circuits and ground faults. Okay? The second protection, the motor overload protection, does exactly what it sounds like. It protects against overloads of the motors. And what that does is protects the motor windings, and the wire going from the disconnect to the motor. It's sized smaller than the first protection. The first protection is if there is a true short circuit or a true ground fault. It's going to trip the breaker. That short circuit ground fault protection is always going to be a little bit larger on that motor, and that's going to allow for the inrush of current. The motor overload protection is going to be a little bit smaller, sometimes a lot smaller, and the reason is that is going to protect the internal parts of the motor. We don't want the motor itself burning up. Now let's learn how to size it. What size short circuit ground fault protection would you select for a 5 horsepower, 208 volt AC 3-phase motor terminating to 60° C terminals with a nameplate FLA rating of 26 amps using an inverse time breaker? You will never size short circuit ground fault protection from the nameplate or FLA rating. I will say this one time, that if the FLC is printed on the nameplate, you can use it, but it has to say FLC, okay? FLC, it's got to say full load current. You could use it if it happened to be there. But what we're going to do is like we normally do to find our FLC, and we're going to head to our FLC tables. So let's flip to our FLC tab. Using table 430.250 because it's a 3-phase motor, what is our FLC? We start on the left-hand side for our horsepower, then we come off and T with our voltage, and we're going to select our FLC. In this case, it's 16.7 amps. Now we have to go check out a new table, okay? So everyone head to 430.52, page 308 in the 2017, and page 319 in the 2020. When we get there, the first thing that we do is we read our black bold heading. It says maximum rating or setting for motor, branch circuit, short circuit, ground fault protected devices. I feel like we're in the right place. Now on the left-hand side is going to be your type of motor, whether single phase or polyphase. Then across the top, you're going to notice different type of devices. There's a non-time delay fuse, a dual element fuse, an instantaneous trip breaker, and an inverse time breaker, which is the breakers that we normally use. So let's go ahead and answer our question. First, we find our motor in the motor column. We go down to polyphase. I want to let you know that that just means 3-phase. Now we come over and tee off with our type device. In this question, it was an inverse time breaker. Now what we do is we take that multiplier and do the math. We take our FLC, which is 16.7, we multiply it by 2.50. That is going to give us a new amperage to size our breaker by of 41.75. All right, so we took and we did our math. Now, do they make a 41.75 amp breaker? And the answer is no. I want you guys to know that with motor short circuit ground fault protection, you can use the NEC size up standard breaker. When we get to motor overload protection, you cannot. So with short circuit ground fault protection, you can use the NEC size up breaker. So we head to table 240.6a and we check and we find a breaker that is the NEC size up from 41.75 amps. And in this case, it's going to be B. What size short circuit ground fault protective device would you select for a 7.5 horsepower, 115 volt AC single phase motor terminating to 75° C terminals with a nameplate FLA rating of 71 amps using a dual element fuse? Now, we never size short circuit ground fault protected from the nameplate or FLA rating. We're going to use the FLC. So we go and we find out what our FLC is. Now we head to table 430.248. What is our FLC? We start on the left-hand side, find our horsepower, come across to our voltage, and we're going to find that our FLC is 80 amps. Now we head to 430.52 and find our multiplier. Starting on the left-hand side and finding our motor, we come over and we tee off with our type of device. Then we're going to find that it's 175% for dual element fuses. Remember, this is just another demand factor. So we take 80 multiplied by 1.75. That's going to give us 140 amps. Now we head over to 240.6a and select the next size up. And in this case, it's going to be B. What size motor short circuit ground fault protective device would you select for a 7.5 horsepower, 208 volt, 3-phase motor terminating to 60° C terminals with a nameplate FLA rating of 26 amps using a dual element fuse? We will never size short circuit ground fault protection from the nameplate or FLA rating. First thing we do is we find our FLC. Now we head to table 430.250. What is our FLC? Starting on the left with horsepower, coming over to the voltage, we find that our FLC is 24.2 amps. Now we head to table 430.250 and find our multiplier. Starting on the left for polyphase and then coming over to our type of device, we're going to find that it's 175%. We take our FLC, multiply by 1.75. That's going to give us 42.35. Now we head to table 240.6a and select the next size up. And we select B. What size short circuit ground fault protection would you select for a 5 horsepower, 115 volt AC single phase motor terminating to 75 degree C terminals with a nameplate FLA rating of 60 amps using an instantaneous trip breaker? And I love this one here. You're going to think it's hilarious. So we never size normal short circuit ground fault protection from the nameplate or FLA rating. First thing that we do is find out what our FLC is. We head to table 430.248, what is our FLC? Starting on the left-hand side with our horsepower, coming across to our voltage, we're going to find that the FLC is 56 amps. Now we head to table 430.52 and find our multiplier, starting on the left-hand side, finding single phase, then coming across to the type of device. In this case, we're going to find that our multiplier is 800%. So we take our FLC, we multiply it by 800. And we take 56 multiplied by 8, and that's going to give us 448 amps to size our device by. Now we're going to head to table 240.6a. We're going to select the next size up, and we're going to select a 450 amp overcurrent device. Now, just for fun, we're going to take the same question and we're going to size the conductors, okay, and show you how outrageous this is. So we size the conductors like this. We would take that 56 amp FLC, multiply it by 125%. That's going to give us 70 amps. Now we head to our primary ampacity table. We size the wire. It's going to be a number 4. So legally in this situation, you could put it on number 4 wire on a 450 amp breaker. Okay. Now that would be the original breaker that you did back at the original panel. You would still have overload protection, but still, it's just outrageous to think that you could put number 4 wire on a 450 amp breaker. Now we're going to learn about motor overload protection. What size overload protection would you select for a 5 horsepower, 120 volt single phase motor terminating to 75 degree C terminals with a nameplate current rating of 54 amps? We always size normal motor overload protection from the nameplate FLA current rating, not the FLC that are listed in those tables. Let's all turn over to page 304 in the 2017 and page 315 in the 2020. All right, when we get to 430.32a, it states that for motors that are more than 1 horsepower shall be protected against overload protection by one of the following means. And it lists A1 through A4. We're only going to be dealing with part A1. It says separate overload device. A separate overload device that is responsive to motor current. This device shall be selected to trip at no more than the following settings. So the only things that we have to focus on here are these 3 things that are listed right under there. Motors that are marked with a service factor of 1.15 or greater. And if you look all the way over to the right-hand side, it said that it has a demand factor of 125%. The next one says motors that are marked with a temperature rise of 40 degrees C or less. That's at 125%. And then all other motors, and they only require 115%. So a way to simplify it, if your motor is not marked with a service factor of 1.15 or greater or a temperature rise of 40 degrees C or less, it's going to fall under the all motors category and your demand factor is only 115%. So let's look at our question again. There's no service factor listed and there's no temperature rise listed. So it will fall under all other motors. So we just multiply. We take our FLA, which was 54 amps, multiplied by 1.15. That's going to give us a new total of 62.1. Now, do they make a 62.1 amp breaker or fuse? No, they don't. So the question is, can we use the next size up? And the answer is no. With motor overloads, you are not allowed to use the next size up. So just remember, short circuit ground fault protection, everything's normal, we can use the next size up. When sizing motor overloads, however, you have to use the next size down. So we still head to our table 240.6a, and we're going to select the next size down, which in this case is going to be A. Great job. What size motor overload protection would you select for a 7.5 horsepower, 208 volt AC 3-phase motor terminating to 60 degree C terminals with a nameplate FLA rating of 22 amps? Remember, we'll always size normal overload protection from the nameplate FLA rating, not the FLCs that are listed in those tables. Also, we have to remember to use the neck size down protective device for normal overload questions. So let's look at our question again. There are no service factors and no temperature rise listed. So it's going to fall under all other motors. We take our FLA, multiply it by 1.15, that gives us 25.3. Now we head over to 240.6a and select our device. And we should select the next size down, which is going to be a 25. Great job. What size overload protection would you select for a 5 horsepower, 120 volt AC single phase motor terminating to 75 degree C terminals with a nameplate current rating of 54 amps and a marked service factor of 1.18? All right, so we're still going to go back to the same section, but we need to check what the demand factor is for a service factor. So we head over, we always size normal short circuit ground fault protection from the FLA rating, not the FLC that are listed in our tables, and we're always going to select the next size down. So let's look at our question again. There is a service factor listed. We're going to go back to our code book here, and we're going to select a 125% multiplier. We take that 54 amps multiplied by 1.25, that's going to give us 67.5. We're going to head to 240.6a using our OCPD tab, and we're going to select the next size down, which in this case is going to be D. What size motor overload protection would you select for a 3 horsepower, 230 volt AC single phase motor terminating to 75 degree C terminals with a nameplate FLA of 15 amps and a temperature rise of 37 degrees C? We always size normal motor overload questions from the nameplate FLA, not the FLCs listed in these tables. And we always use the next size down when selecting our protective device. Now let's look at our question again. In this case, there is a temperature rise. So we head back to our code book. We select our multiplier of 125%. We take 15 multiplied by 1.25. That's going to give us 18.75. We head to 240.6a, and we're going to select the next size down, which is going to be D. Great job. What size overload and short circuit ground fault protection would you select for a 5 horsepower, 230 volt AC single phase motor terminating to 60 degree C terminals with a nameplate FLA rating of 23 amps using fuses for the overload protection and an inverse time breaker for the short circuit ground fault protection? So first let's size our overload protection. We use our nameplate FLA rating for it. There's no service factor or temperature rise listed, so it falls under all other motors. We take our 23 amps, multiply by 1.15. That gives us 26.45. Now head to 240.6a, select the next size down. That's going to be a 25. Now let's size our short circuit ground fault protection. We're going to use our FLC. In this case, we have to look it up. In this case, we are dealing with a single phase motor, so we're going to go to 430.248. We find that our FLC is 28. Now let's head to table 430.52. We're going to select our multiplier. We take 28 multiplied by 2.50. That's going to give us 70. We head to 240.6a. We select the next size up, and it's going to give us a 25 amp overload on a 70 amp short circuit ground fault protection. Great job. Now we're going to learn the 3 different tables that we size almost all of our grounding and bonding conductors. There are 3 classifications of grounding and bonding conductors. The first one is the grounding electrode conductor. That's the GEC. That is the wire that's physically installed from, we'll say, the ground rod all the way to the panel, or the footing ground all the way to the panel. The second classification are bonding jumpers. Now, a good example of a bonding jumper is the main bonding jumper. And I don't know if you've ever seen that green screw in the back of a panel. You know how sometimes we'll screw that screw in if we're at the first point of disconnect? That screw right there is actually called a main bonding jumper. They can also be made of wire, and you may have also seen them as the strap that you turn into and connect the neutrals and grounds if you're at the first point of disconnect. Or sometimes you just use that little strap, which is made up of a piece of copper, and we're going to use that to bond the frame of the panel. That's one example of a main jumper. There's system bonding jumpers, supply side bonding jumpers. We're going to learn how to size those today. And the third classification is the equipment grounding conductor. That's the EGC. And that is going to be the conductor that we run with our circuits, isn't it? You know, it'll be either green or bare or stranded or solid. It could be any one of those variations. A good example is inside of a Romex jacket. Typically, it'll have a hot, a neutral, and a bare ground, won't it? That is an example of an equipment grounding conductor, and we're going to learn how to size those today. Let's learn about sizing grounding electrode conductors. Everyone head to table 250.66. It's on page 116 of the 2017 and on page 123 of the 2020. Pause the video now if you need to. So the first thing we get there is we check the black bold heading and make sure that we're at the right table. And I cannot stress to you enough, the next 3 tables that we're getting ready to learn almost look identical. And if you don't read the black bold heading when you get to the table, you can be off in a heartbeat. I mean, these 3 tables look almost identical. So when we get to our table, it says 250.66, grounding electrode conductor. Great, I feel like we're in the right table. So starting on the left-hand side are going to be 2 columns, and on the right-hand side are going to be 2 columns. Let's break those down now. So on the far left-hand side, those 2 columns are the size of the ungrounded hot conductors. So whatever your service is, these are based off the size of the ungrounded hots. You're going to have a copper column and an aluminum column. Okay? So if your main conductors, your hots are made of copper, you're going to select from the copper side first. And then when you come over to the other side, you're going to select depending on the make and composition of the grounding electrode conductor itself, you're going to select from copper or aluminum. Okay, so let me be very clear and very slow right here. If our mains are made of copper, we select from the copper side. If our mains are aluminum, we select from the aluminum side. Then there's a second conductor involved. It's the actual GEC itself. And we have to cross over and make sure we select from the right column, whether copper or aluminum. Because it's very easy to go copper and then want to go straight over to copper. But whatever your real world scenario or whatever your question states, you have to be very diligent to select from the respective column here and then jump over and select from the proper column here. But we're going to do a bunch of practice questions and you'll be a pro by the end of it. Now let's all flip back 1 page. Okay? Flip back 1 page to article 250.66, okay? And we're going to do a little bit of highlighting. So we flip back 1 page, and we're going to start at the beginning of 250.66, the actual article, okay? And if you read the black bold heading, it says size of alternating current grounding electrode conductors. We're going to do some very strategic highlighting here if you're allowed to do highlighting in your state. So right underneath it at part A, I want you to highlight in the black bold heading the word rod, pipe, or plate. Rod, pipe, or plate. I want you to highlight that. Then I want you to go down to the bottom of that paragraph, and I want you to only highlight 6 AWG copper. 6 AWG copper. Highlight that. And we're done here. Now let's go to part B. And I want you to highlight the word concrete encased electrode in the black bold heading of part B. Then when you're done with that, I want you to go down to the bottom of that paragraph and highlight 4 AWG copper. Then we're going to go to part C. And I want you to highlight the word ground ring. And depending on what code book you're in, for this one, we have to flip back a page or 2. Okay? We have to flip over to 250.52. I want you to flip a couple pages back to 250.52. And it's in part A, and it's part 4. And you'll see the black bold heading that says ground ring. At the bottom of that paragraph, I want you to highlight the 2 AWG. Because that's the minimum size it's allowed to be. And all of this is going to make sense here in just a moment. Because there's 2 ways that we size grounding electrode conductors. And I think this is where most people get lost. Because I know when I first got started, I didn't know the difference. And I guarantee I did it wrong every time. but there's two classifications of grounding electroconductors. You're either going to size it based off of table 250.66 if the electrode is not mentioned, or if the electrode is mentioned in your question or in your real world scenario, you're likely going to be using article 250.66, parts A, B, or C. And we're going to go through this step by step. Let's get to it. All right, now let's reiterate these ground rules for sizing grounding electrode conductors. If no electrode is mentioned, the type of electrode, so if it doesn't say ground rod or footing ground or anything like that, you're going to use table 250.66 at face value. If the electrode is mentioned, we first need to check 250.66 A, B, or C. If the electrode is not mentioned in 250.66 A, B, or C, you would go back to the table. But usually if there's an electrode mentioned, you're going to be using A, B, or C. And this is a very easy one that you can get on your test. Once you learn how to do this, you get those grounding and bonding questions, you'll be able to flow right through them. You're one step closer to being a licensed electrician. What size copper grounding electrode conductor would you select for 100 amp service with number 4 main copper service conductors? So the first thing we're going to look at our question doesn't mention the type of electrode. No, so we're going to use table 250.66 at face value. So starting on the left-hand side, we're going to select the type and size of the service conductors. So we have to go back to our question. It says copper service conductors, so we're going to start on the copper side. Then what we're going to do is go to the right side and we're going to select the right type and size of the GEC. So when we cross over to the table, we have to look back at our question and it wants a copper grounding electrode conductor. So we go from copper to copper and we make our selection. So we come across, when we tee off, we find out that we're going to select a number 8. Great job. What size copper grounding electrode conductor would you select for a 225 amp service with 3/0 main copper service conductors? So the first thing, does it mention the type of electrode? No, so we're going to use table 250.66 at face value. So starting on the left-hand side, being careful to reread our question, in this case we're going to start on the copper side. Then when we go to make our GEC selection, we're going to slide over to the right, we're going to look at our question again, and we're going to select from the copper side over here as well. And in this case, we're going to find that we would be required to have a number 4, and we would select C. Great job. What size copper grounding electrode conductor would you select for a 400 amp service with 400 kc mil main copper service conductors? First thing, does it mention our type of electrode? No, so we're going to use table 250.66 at face value. Starting on the left-hand side, selecting the type and size of our service conductors, and in this case it's copper. Then when we cross over, we're also going to be selecting from the copper side, and we're going to select a 1/0. D. Great job. What size copper grounding electrode conductor would you select for a 400 amp service with parallel 2/0 copper main service conductors? First thing, does it mention the type of electrode? No, so we're going to use table 250.66 at face value. Normally we start on the left-hand side and then make our selection, but we're dealing with parallel conductors, and this is how we handle it. So let's head to Chapter 9, Table 8. First, we need to find the approximate area of one 2/0 conductor, just like we did with voltage drop. So we go down on the left-hand side, we're going to come over, and we're going to find the area in circular mils, just like we did for voltage drop. So each 2/0 copper service conductor, starting on the left-hand side to find our wire, then coming over 2 small columns to the circular mils and area, we're going to find that each 2/0 is 133100. And that is in circular mils. But we have 2 of those conductors, so how we handle this is we just multiply it by 2, and that's going to give us our total C mils, okay? Once we get our total C mils, we're going to head back to our original table, back to 250.66, and we're actually going to find where that conductor falls in our table. Now this is listed in C mils. If we wanted to turn it into kc mils, we would just divide by 1,000, but it's pretty easy if you just leave it in the C mils. So starting on the left-hand side, that is now the size of your service conductor. We've converted it to just one conductor. We found the area of one of the parallels, multiplied it by 2, and now we're just treating it as one large conductor. So we go down through here and we find where 266,200 C-mils falls. And in our case, it's going to fall in the 3/0, but not over 350. Because remember, this table's listed in kc-mil, so that would equal 350,000 C-mils. So it falls right there in the 3/0 to 350 section. So what we do is we go over, now we have to be careful again. Our question wanted copper and copper. So we make our selection, and we're going to select a number 2. What size copper grounding electrode conductor would you select for a 200 amp service with 2/0 main copper service conductors with a ground rod as the grounding electrode? First thing, does it mention our type of electrode? It does, so we may not be using table 250.66 at face value. Let's head back to 250.66, reading the black bold heading using our keywords. We've already done our highlighting, so we're going to find that part A states rods, pipes, or plates. Now looking down to our other highlighted mark, or at the bottom of the paragraph, we're going to find that it's not required to be larger than a number 6. Great job. What size copper grounding electrode conductor would you select for a 200 amp service with 2/0 main copper service conductors with a concrete encased electrode? First thing, does it mention our type of electrode? It does, so we may not be using table 250.66 at face value. The first thing we do is we head straight back to section 250.66, reading in the black bold headings, looking for keywords. So we've already done our highlighting, so this should be very simple. When we look at it, we're going to see that part B states concrete encased electrode. Then all we have to do is go to our second part of our highlighting, and we find out that it is not required to be any larger than a number 4. Now, this supersedes what the table says. That's why we have to be very careful, and this is where a lot of people get the answers wrong on their actual examination, because this value over here in Article 250.66 actually supersedes the table. So if the type of electrode's mentioned, go check A, B, or C and see if the answer's listed there. And we're going to select C, a number 4. What size copper grounding electrode conductor would you select for a 100 amp service with number 2 main aluminum service conductors? First thing, does it mention the type of electrode? No, so we're going to use table 250.66 at face value. Starting on the left-hand side, being very careful to check the type and size of our service conductors. In this case, it's aluminum, so we have to start here in aluminum. We go down to where our conductor falls, then we have to be careful. It wants a copper GEC, which is very common. Main service hots, and then use a copper grounding electrode conductor. So then we come over to the right to being sure to be in the copper column, and we're going to make our proper selection. And we select A. What size copper grounding electrode conductor would you select for a 225 amp service with 250 kc-mil main aluminum service conductors? First thing, does it mention the type of electrode? No, so we're going to use table 250.66 at face value. Starting on the left-hand side with the type and size of service conductors, very careful, it's aluminum. Then when we make our crossover, being sure to go to the copper side because that's what it's requesting, we make our selection, and we're going to find that it's not required to be larger than a number 4. What size copper grounding electrode conductor would you select for a 400 amp service with 500 kc-mil main aluminum service conductors? First thing, does it mention the type of electrode? No, so we're going to use table 250.66 at face value. Starting on the left-hand side with our type and size of service conductors, in this case aluminum. Then when we cross over, it's asking for a copper grounding electrode conductor. When we look through there and we tee off, we're going to find that it's not required to be larger than a number 2. Now let's learn how to size equipment grounding conductors, EGCs. And for that, we're going to use table 250.122. It's on page 125 of the 2017 and on page 133 of the 2020. And I love this table because it's so easy to use. There's not all these crazy exceptions. It's very simple. So when we get there, the first thing that we do is we read the black bold heading to make sure we're in the right table. Minimum size equipment grounding conductors. Great, I feel like we're in the right table. Now this table's laid out like this. It has the size of the overcurrent protective device on the left, then the size of the EGC on the right. So we have our overcurrent protective device in amps, and then we have a copper and aluminum. So we just have to be careful when we cross over to make sure we select, from the proper column, but it's really simple. Size of the breaker or fuse on the left, copper or aluminum on the right. Let's get to it. What size copper equipment grounding conductor, EGC, would you select for a service with a 200 amp main breaker and 4-aught copper conductors? Doesn't matter what the conductors are. In this case, it's always based off the size of the overcurrent protective device. So we head to table 250.122 using our EGC tab. We always size our EGC based off the overcurrent protective device size. So in this case, what should we use for a copper at 200 amps? When we slide over, being sure to select from the copper side, we're going to select A. Great job. What size aluminum equipment grounding conductor would you select for a service with a 100 amp main breaker with number 2 aluminum conductors? So we head to table 250.122 using our EGC tab. Then we're going to base our EGC off the size of the overcurrent protective device. And we're going to be sure to cross over to the aluminum side, and we're going to select D. Great job. Now we're going to learn about sizing bonding jumpers. This is done in table 250.102C1. Now there's not a tab for this one, but if you watch my how to make your own tabs video that is back in week 1, it will show you how to make your own tabs. And this is one of the ones that I highly recommend making. I call it bonding jumpers or something like that. But to head to this table, we're going to head to page 119 of the 2017 and page 127 of the 2020. When we get there, we check the black bold heading to make sure we're in the right table. And when we look at it, it says grounded conductor, main bonding jumper, system bonding jumper for alternating current. Great, I feel like we're in the right table. Now this table is laid out very similarly to the GEC table, the 250.66. That's why you always read your black bold heading to make sure you're in the right table. So we're going to have the size of the ungrounded hots on the left, size of the bonding jumper on the right. We have copper and aluminum, and we have copper and aluminum. So these questions are laid out very similar, but we have to make sure that we're in the right table. What size copper main bonding jumper would you select for a 200 amp service with 2-aught copper conductors? So we're going to head to table 250.102C1. You're going to size the main bonding jumper based off the largest ungrounded service conductor. Starting on the left-hand side, we select our type and size of the service conductors. In this case, it's copper. Then on the right side, we're going to go over and we're going to select a copper main bonding jumper. And we're going to select A. Great job. What size copper main bonding jumper would you select for a 100 amp service with 1-aught aluminum conductors? So we're going to head to table 250.102C1. We're going to size our main bonding jumper based off the largest ungrounded service conductors. Starting on the left-hand side, we're going to be careful to select our type and size of the service conductors. In this case, it's aluminum, so we start on the aluminum side. Then we're going to cross over to the copper side. And we're going to be careful to select C. Now let's learn about burial depth of conduit. What is the minimum cover requirement for a piece of rigid metal conduit that passes under a driveway of a one-family dwelling unit? When dealing with most burial depth questions, you're going to be using table 300.5. It's on page 137 of the 2017 and on page 143 of the 2020. So let's go ahead and create a tab and call it pipe depth, okay, or burial depth. However you like to name it, you can create your own tab if you watch my video on how to create them, and you can create your own tab for this. It makes it easier. So let's go ahead and look at the table together. So the first thing that we do is we check the black bold heading. It says minimum cover requirements is 0 to 1,000 volts. I feel like we're doing good. With that being said, on the left-hand side is going to be our location type. So you have to be careful to see if your question states a specific type. In our question, it says one family dwelling. Okay, so that makes it easier. Also, we're dealing with a driveway. I do want to note if your area is not mentioned specifically in the lower part of this table, the first one that you come to there on the left-hand side says all locations specified, or excuse me, not specified below. So if your location is not specifically specified below, you're literally going to use the catch-all area that says all locations not specified below, and then come over and tee off with the respective depth. Now going across the top, looking at the black bold headings, you see column 1. It's for direct burial cables or conductors. Column 2 is for rigid metal conduit or intermediate metal conduit. Column 3 is for non-metallic raceways, okay, like PVC. Column 4 is a very special column for 120 volt circuits with GFCI protection, okay, and also column 5 is going to be if you're dealing with low voltage or landscape type lighting, okay? With that being said, what you can do is use this table. You just very carefully pick apart your question, and then you look and see if your specific area is listed on the left, and then come over and tee off with the type of conduit that you're using. So how deep should ours be? So we start on the left, and we look, and under 1 and 2 family dwelling unit driveways, now we're going to come over and we're going to tee off with rigid metal conduit, which is column 2. We're always going to be using the inches in the United States, and we're going to find out that it's not required to be deeper than 18 inches. Now that's to the top of the pipe. So from the top of the pipe to grade, whatever the finished grade is, it is allowed to be not less than 18 inches deep. What is the minimum cover requirement for a piece of PVC that passes under a parking lot in Johnson City, Tennessee? So the first thing we do is we use our pipe depth tab. We're going to select our location on the left. And if we come here, we're going to find that there is a under streets, highways, roads, driveways, and parking lots. Okay, and those driveways specified in this one are not your 1 and 2 family dwelling units that are down below. These are just general driveways going to other places. But in this case, we're going to use that one because it also lists parking lots. Then we come over and we tee off with non-metallic raceway, which is going to be our PVCs. And we're going to find that it is required to be not less than 24 inches. And we're going to select C. Now we're going to cover one more quick thing. Classified locations is a very deep section, but you can mainly use your keyword and index process to find every one of those type questions. But I'm going to let you highlight right now some things that are very common in tests and can give you some pretty quick answers if you highlight it correctly. So every test that I've ever taken has had a classified location question test. And it's really just a lookup question, but I'm going to give you guys an edge on it, okay? So everyone close your code book. And let's use the Class 1 Location tab to flip to 501.1. When we get to 501.1, there's something that I want you to highlight in this paragraph. I want you to highlight at the bottom of the paragraph of 501.1, I want you to highlight flammable gases or vapors or flammable liquids. Highlight just that right there. Flammable gases or vapors or flammable liquids. Now everyone flip to page 364 in the 2017 and page 378 in the 2020. And I want you to head and highlight to 502.1. And I don't want you to highlight the whole thing. The only thing I want you to highlight is at the bottom of that paragraph, I want you to highlight the word combustible dust. Highlight the word combustible dust. Then when you're done with that, I want you to flip to page 369 of the 2017 and page 383 of the 2020. And at the bottom of that paragraph of 503.1, I want you to highlight the words ignitable fibers / flyings. Ignitable fibers / flyings. And these are very common questions on an exam. Also, I go ahead and make a tab for each one of these, and I show you how to do that in my how to highlight your code, how to tab your codebook video. That way, if I have any of these keywords, I can flip right to it. What article in the codebook would you use when wiring in a location where fired or explosion hazards may exist due to combustible dust? Now, when you see something like this is when you get excited, but you slow down. You know, you're in the testing center, you see the question, you're like, I know this, I can do this, but you slow down and make sure you make the right selection. How I do it is I usually go to our first tab in order. The first one is the Class 1 location. Go ahead and read it. Does it say anything about combustible dust? No, it doesn't. So now I'm going to flip to the second tab, okay, which is going to be a 502 section. And let's read it. Does it give us what we want? It gives us exactly what we need. And we're going to select B. Great job.
All right, y'all, congratulations. You have completed the 301 Electrical Code Coach Training Program. I'm so proud of you, and I'm so excited for you. First off, I want to thank you. I want to thank you for all your hard work, the late nights, the long days, grinding early in the morning, whatever it took to finish the program. I'm super excited for your future, and I want to thank you for allowing me to be a part of it. Second, I want to let you know that I'm here to help you in any way that I can. I'm here to help you in life. I'm here to help you in business, here to help you get your license, here to help you if you get in trouble out in the field. If I don't know the answer, I probably know someone who does. I'm available all the time by email at electricalcodecoach@gmail.com. You may have to try multiple ways to get a hold of me. The Gmail is probably the best way, but if you don't hear a response, send another email. You are never a bother to me. This is what I do. This is my life. I'm here to help you get to the next level and higher and higher. Finally, I want to challenge you. You've been given a unique set of skills and connections, skills that I don't have, connections that I don't have. I want you to use those connections and those skills to help someone else. Listen, there are a million takers out there, and we are full to the brim of bad electricians. So I want you to be a giver. I want you to help others, and I want you to watch what it does for you, and I want you to strive for excellence in your work. My bargain is that I can invest in you and you can invest in someone else, and it can be value multiplied. Listen, I want you to strive for excellent work. Not every job will be pretty, but I want you to do everything you can to make it technically correct. You can do it. You're an electrician. You're at the next level. That's what sets us apart from everyone else. And listen, if you make mistakes, admit them, learn from them, and keep on pushing. You are as close as you've ever been to being a licensed electrician. You really have two options. Push harder or quit. You decide. Hey everyone, welcome back. I am the Electrical Code Coach from electricalexamcoach.com. And this is lesson 1.1 in our video series. And in this lesson, we're going to do a short introduction. We're going to teach you about the course layout and show you how to use the course. Let's get to it. A little bit about me. I'm the baby of 6 children, and we grew up absolutely dirt poor. I wouldn't trade anything for it now. It's a large portion of who I am today and why I am so hungry. But I attribute all of my success to the 3 G's: God, grit, and grind. And we hope to pass some of those along to you. I've got 4 children of my own, and they are my reasons, or they're some of them. And we want to help you find your reasons, because you're going to need to know why you're doing this. Why are you getting your license? Why are you getting your certification? Because when work's hard and the boss is yelling at you and you're still wanting to study and you're tired and you've got football practice or whatever it is with the kids, you're going to need those reasons to push you through this program when times get hard and you still need to study. I've got 18 licenses and certifications, international, multi-state, federal licenses. I also sit on 7 boards, colleges, cities, international organizations, blah, 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 blah. We're not going to tell you any more about me in this program. This program is going to be all about you. So if you're looking for a program where I tell a lot of stories or fill you with a bunch of fluff, this program is not for you. We're into system after system, process after process. We just want to see you win. The only thing that you need to know about me is that I care. People don't care how much you know until they know how much you care. I'm getting ready to teach you a ton of things and blow this NEC book out of the water for you. But if you don't know how much I care about you, about your family, why I'm doing this, I want to see you win. Listen, I've dedicated my life to it. You can shoot me a call or a text anytime. I get back as quickly as I can. You also can shoot me an email and I will respond. My life is dedicated to helping you become everything that you can be in life and in the electrical industry. So before we move on in this program, I need you to understand and know just how much I care. Now let's learn about the course layout. We're going to teach you about the keyword and index process and how to look up questions in the book. We're going to teach you about load calculations, and we load them at the front end of the program, because inside there, we're teaching you a lot of little processes that will serve you throughout the program, like what a demand factor is. We're going to teach you about box fill, pipe fill, voltage drop, motor calculations and sizing motor overloads, and motor short circuit ground fault protective devices. We're going to teach you about classified locations, transformers, sizing grounding and bonding conductors, OSHA, NFPA 70E, and business and law strategies. We're going to teach you a lot of other things along the way. Some of them we teach you in videos, and some of it we teach you inside of the quizzes. Some of them you're going to commit to memory, and a lot of them you're going to commit to memory the process on how to get the answer. Now let's learn about the website and how to use it. You can do it on your smartphone, computer, or tablet. One thing you'll notice right away is we have one price for all access, all cycles. So you don't have to worry about what level you have. Once you decide whether you want to do monthly, 3-month, 1 year, or even lifetime, it unlocks the entire website. You can see membership options at this link. Once you get the pro version, you can click on this link to continue the program, or you can come up here to this pro version link. Once you open the pro version, you're going to notice that it's very simple. We do not have a lot of distractions or bells and whistles or fluff content that you don't need for your exam. If you're in the 2017-2020, you're just going to keep scrolling down. If you're in the 2023, you're going to click here and it's going to take you to the same interface with a few different lessons that make it 2023 compatible. After you do lesson 1, you're going to click on lesson 2. When you get to lesson 2, you'll notice that you have the videos and the quiz. Always do the videos first. Once we scroll down and find our videos, you're going to do them in order from top to bottom, and we're going to watch them right here in the player. One beautiful thing about our program is you can do it full screen. You also can do something that no other program offers that I know of. You can download these videos for offline access. That is included in your pro version membership. Once you get through with all of these videos, you're going to come down here and take the lesson 2 quiz. Once you start the lesson 2 quiz, you're going to select an answer and click the check button. Now, all of our answers are going to show up right then to tell you if you've got it right or wrong, and down below is where you have your custom feedback. Some of the questions have individual videos that we've made to answer that question or a similar question just like it. So you'll just click play.
What is the resistance?
And in this case, it's going to go through and answer this exact question in video form and give you a detailed breakdown. If you're not able to watch video or you prefer to learn by text, the text will show up underneath it so you can learn that way as well. Then you'll select the next question and go on through the program. Once you've finished all of the video lessons, and don't skip any of them, it's very important that you finish them all. They're very short and very succinct. But once you finish them all, then you're going to go to the ECC Testing Center. And this is where the magic happens. We go through and we have topical quizzes, grounding, bonding, conductors, cables. Then we have our grind out quizzes, which are just question after question after question. Then you can come down and take your simulated exam. Once you work through all of the pro version and all of the ECC Testing Center, you're ready to take your exam and see where you're at. You'll notice in the bottom left hand of each video that you're going to have your compatibility for that video. If you notice a video like this that has the 2023 crossed out, then that means you're not on the 2023 version on the website. You need to go back to the pro version, scroll to the 2023, and go through it. If it's cross-compatible with all of them, you're going to have the 2017, 2020, and 2023 logos down in the bottom. That's the end of lesson 1.1. You can head over to electricalexamcoach.com to sign up for the pro version. I am the Electrical Code Coach, and my bargain is that these videos will add value to you, and you will in turn add value to others. Let's get to it. Hey everyone, welcome back. I am the Electrical Code Coach from electricalexamcoach.com, and this is lesson 1.2 in our video series. And in this lesson, we're going to be learning all about the keyword and index process. Let's get to it. The keyword and index process is a 3-step process. Step 1, we're going to read the question and the answers twice. Sometimes when you read a question the first time, you'll think that it's leading you to a certain part of the index or a certain part of the code book. But when you reread it, you'll realize that it was actually asking something else. And you always want to read your answers twice, because once we do get to the correct section of the code book, you're going to need to know what the answers are, and hopefully it will pop off the page for you. Step 2, we're going to pull all the keywords from the question. You're going to be in a testing center setting, and they're going to give you a pencil and something to write on. You can write down the keywords, or you can continue to look back and forth at the screen until you feel comfortable with where you are in the book. I highly recommend that while you're using my program, practice doing both. Practice writing down the keywords and then practice just looking back and forth at the screen until you find what you're looking for. And step 3, and probably the most important, is you're going to ask 2 questions. Where am I and what am I wiring? The first thing you're going to ask is, where am I? Am I in a kitchen? Am I in a bathroom? Am I outdoors? Am I indoors? And what am I wiring? If you can focus on that, that is going to give you the overall theme, and that'll help you get there quickly in the code book. Let's get to it. Now let's use the keyword and index process to answer this question. Step 1, we're going to read the question and the answers twice. Step 2, we're going to pull all the keywords. I like to start with about 2 or 3, but if the question gets really tough, you may have to go for more. Let's start with disconnecting, service, and maximum. And step 3, we're going to answer these 2 questions. Where am I and what am I wiring? Well, in this scenario, I'm going to be outside, aren't I, if we're wiring a service? And that answers my question. I'm wiring a service. And that's going to help us hone in on the theme of the question. Now, when we look at our possible keywords, the one that pops out the most is going to be service. Let's start there and see if we can find anything. Let's start with S for services. The index is located at the back of your code book. Pause the video now if you need a moment to get there. When we get to the index, we notice that it's in alphabetical order. And we're going to use those black bold headings to look for our first keyword. And in this case, it's service. And when we get to the S's, we notice that there are a lot of black bold headings about services. Service conductor, service entrance, service lateral. We want to try to be as specific as possible. So we're going to look for something about service or services. And after we look for a few moments, we'll notice that we find services. Now, underneath that black bold heading, you're going to notice some lighter headings. And those are going to be what you look for with your second keyword. And in this case, I would go with disconnecting means first. So we look for D underneath that services subheading. And sure enough, we find something about disconnecting means. When we look, it gives us a couple of different code references. So we're going to start with the first one first, and then we'll go to the second one. One thing I want to note out here is that while we go to this first reference of 230.71, you need to keep your hand or a piece of paper in the back of the book. So just in case it's not the reference we need, we can quickly flip back to the index and go to the next reference. Once we head to 230.71, this is when we need to slow down. We're going to take our time and read the black bold headings. You're always going to navigate your code book using the black bold headings. You do not have a lot of time in the testing center. So you've got to decide what paragraphs you're going to read because you don't have time to read large sections of the code book. So we're going to use keywords and the black bold headings to decide whether or not we're going to invest reading about this topic. And sure enough, when we get there, we notice that the black bold heading says maximum number of disconnects. We have multiple keywords here, so we're really going to slow down. And we're going to take our time and hone in on this. If you're in the 2017, when you read that paragraph there, you'll find your answer in the very first paragraph. If you're in the 2020 or the 2023, you're going to notice that you're going to have to go to the next black bold heading, and it has more keywords, and you'll find your answer inside of that paragraph. If you think you're in the right section of the code book, take a minute, read the page before, read the page after, looking at the black bold headings to find out and decide which paragraphs you want to read. And in this case, we find our answer and select D. Great job. Let's run the replay on this question and learn a few more things before we move on. And the first one is right here in the 4 possible choices. You'll notice that the 4 choices were listed in the numerical digits, but the actual answer was spelled out, wasn't it? S-I-X. And the test makers know that. They'll add things like that in there because they know that you're reading large pages trying to find digits and see if it's the right digits. So they will actually spell the words out or vice versa. That's why we're learning the keyword and index process to decide what paragraphs we're going to take the time and read and which ones we're going to move on from. The second thing we noticed was the importance of reading that question twice. because once we got to the black bold headings, we noticed another one of our keywords jump out from the question. The more familiar we are with that question, the more we're going to be able to be concise in deciding of whether or not we are going to read that paragraph. And finally, in step 3, when we answered the questions, where am I and what am I wiring? We decided that we were wiring a service. And this is going to help you as you continue to grow in the program, because when you get multiple possible choices, you'll start learning the articles. Well, Article 230 is all about services, and Article 250 is all about grounding, which doesn't have anything to do with my question. So the obvious choice here would have been to go to Article 230. And this is really going to be helpful. In this case, they only have 2, but sometimes they have 3, 4, or 5 possible codes that it could be in. And you're going to get faster and sharper. I know you can do it. That's the end of lesson 1.2. And before you go on to the next lesson, I want you to think about the reasons that you're doing this. Are you doing it for your family? Are you doing it for your career? Are you doing it to level up in your professionalism? It's going to be those reasons that keep you moving when things get hard. Let's get to it. Hey everyone, welcome back. I am the Electrical Code Coach from electricalexamcoach.com. And this is lesson 1.3 in our video series. And in this lesson, we're going to be learning all about Ohm's Law. Let's get to it. Ohm's Law was discovered by Georg Ohm, and the relationship states that the current passing through a conductor between 2 points is directly proportional to the voltage across those 2 points, and inversely proportional to the resistance between them. Now that sounds like a mouthful, but we're going to break it down piece by piece and see how it's relevant and fundamental to our getting our license or certification. This picture I keep showing you is the Ohm's Law pyramid. It's also an easy way to remember the Ohm's Law formula. Does anyone know what the E stands for? That's right, it's electromotive force. It refers to the potential difference generated by a source of electrical energy, such as a battery or generator. It's the electrical pressure that pushes or pulls the electrons through the circuit. And just remember, when you're dealing with this Ohm's Law pyramid, that the E stands for voltage. Does anyone know what the I stands for? That's right, the I stands for electrical current, and it's the rate at which the electric charge flows past a point in the circuit. The standard unit of electrical current is the ampere, often shortened to amp, and we're going to call it an amp throughout the rest of our program. The amount of electrical current refers to the quantity of charge passing through the circuit per unit of time. So there's a whole lot of electrons. It's a very large number, but we've all agreed that 1 amp is 1 amp, and that's how we deal with it in amps, or smaller or much larger, as we're going to learn throughout the program. But just remember in this relationship that the I stands for current. Does anyone know what the R stands for? That's right, it's electrical resistance. And it is a property of a material or a component that quantifies how it resists or opposes the flow of electric current. And it's usually measured in ohms. It's letting us know how much it's resisting that electrical flow that we're trying to produce with the voltage, which is also going to affect the amperage that flows through the circuit. All 3 of these are directly related together. Remember that the E stands for voltage, the I stands for amperage, and the R stands for resistance. All right, let's put this all together. The picture I keep showing you is a formula, and it's an easy way to remember this relationship. We have E on top of a division line, and then down below it is the I and the R. Now they're smushed together, and that would be implied multiplication. But just to make it easy to understand while we're laying the basics here, I went ahead and put the multiplication sign in between it. And what this relationship is saying is that as long as we know any of the 2, we can always find the unknown. Now, if you're like me, I don't like a ton of math, but thankfully all the math in this program is 6th grade math. If I can do it, you can do it. Trust me. And what this relationship states is that I know if I know any of the 2, I can always solve for the unknown. If I know I and R, I can just multiply. If I know E and R, I can just divide and it'll let me know what I is. If I know I and E, I can just divide and it'll let me know what R is. And we're going to break this down piece by piece and show you that you can do it. Let's imagine that we have a 120 volt circuit with a 10 amp draw. What is the resistance on this circuit? Well, what I love about formulas is you just plug in what you know.
Draw it exactly how it looks. I put my 120 on top. I know my current. I set it up in this manner. Then all I have to do is divide. I divide 120 by 10, and it lets me know that there should be 12 ohms of resistance on this circuit. Meaning I should be able to put my amp clamp out and read 10. I should be able to put my voltmeter out and read 120. And I should also be able to measure the resistance and measure 12 ohms. If I don't have that, there's something wrong. There's something failed, there's something broken, there's something disconnected, there's something causing more resistance that's gotten in the circuit. It's really great for troubleshooting. And I know that it's going to unlock a lot for you, not only with your testing, but also out in the field. In this case, we have a 120 volt circuit with 12 ohms of resistance on it. What is the amp draw on this circuit? Well, what I love about formulas is we just plug in what we know. We know we have 120 volts. We know that we have 12 ohms of resistance. And we're going to look at this like a division line. We just take 12 and divide up into 120. We set it up like this. 120 divided by 12 equals 10. That lets us know that there should be 10 amps of current on this circuit. Finally, we have a circuit with 10 amps on it and 12 ohms of resistance. What is the voltage? Well, we plug in what we do know. In this case, we're solving for E, and we know that we have 10 amps and 12 ohms. Now all we have to do is follow our Ohm's law pyramid and multiply this out. We take 10 multiplied by 12 equals 120. So E equals 120. Great job. All right, let's do some Ohm's law practice. You can do it. I'm going to go a little bit slow here, so if you want to pause the video and try it on your own, you can. We have 120 volts. We have 16 ohms of resistance. What is the current? That's right, it's 7.5 amps. All we had to do was take 120 divided by 16, and that lets us know that we have 7.5 amps on this circuit. We have 120 volts. We have 15 amps. What is the resistance on this circuit? That's right, it's 8. Great job. All we have to do is take 120 divided by 15, and that lets us know that there is 8 ohms of resistance on this circuit. We have this scenario, and we're solving for voltage. We have 4 amps and 69.25 ohms of resistance. We take and multiply that out, multiply 4 multiplied by 69.25, and that lets us know that we have 277 volts on this circuit. Great job. Now let's learn about another relationship, and that relationship is called pi. And I don't know if you're like me, I love a good piece of pie. In this equation, we know that the I stands for amps and the E stands for voltage, and this equation is saying I times E equals P. But what does the P stand for? That's right, it stands for electric power. Electric power is the rate of energy consumption in an electrical circuit. The electric power is measured in the unit of watts. And this is true on our side of the tracks, that 75 watts is equivalent to 75p. Just like we set up our previous formula like this, we're going to set this one up like this. And I like to think of pi, P-I-E. Makes it easy for me to remember. And just like in the other formula, as long as we know 2 of the 3, we can always solve for the unknown. Let's give it a try. In our first scenario, we have a 1200 watt load on a 120 volt circuit. What will the amp draw be? Well, we just plug in what we know. We know the wattage and we also know the voltage, and we're trying to solve for the current. And just like in the previous formula, all we have to do is divide. So we divide it out and we end up with 10 amps. We have a 1200 watt load with a 10 amp draw. What is the voltage? Well, let's plug in what we know. We know our wattage and our amperage, and all we're looking for is to solve our voltage. So we divide and we get 120. And if we have a 120 volt circuit with 10 amps on it, what will the wattage be? That's right, all we have to do is multiply it out. And when we multiply 10 by 120, that equals 1200 watts. We're going to need to be very familiar with this for the rest of the program. We're going to have to convert back and forth between watts, kilowatts, back down to amps, and everything in between to be able to pass our examination. That's the end of lesson 1.3. I am the electrical code coach, and my bargain is that these videos will add value to you, and you will in turn add value to others. Let's get to it. Hey everyone, welcome back. I am the electrical code coach from electricalexamcoach.com. This is lesson 2.2 in our video series. and we're going to be diving into Article 220 load calculations. And just to clarify what we're doing, we are calculating the demand on a home in order to be able to size the main breaker, the wire, the pipe, the service, and everything that goes along with it. But before we can size all that, we have to know what is the demand on this home. And that's what we're going to be learning over the next few video lessons. Article 220 is broken down into 5 sections. The first one is general requirements. The second one is branch circuit load calculations. The third one is feeder and service load calculations. Part 4 is optional feeder and service load calculations. And Part 5 is farm load calculations. We're going to take you through each one of these piece by piece, except for farm load calculations. The odds of you ever being tested on that are very slim. And if you are, you'll be able to apply everything that I am going to teach you and roll it into a farm load calc. In Article 220 calculations, we're going to be able to round up or down. We're going to round up to the nearest whole number when it's 0.50 and above. And we're going to round down and drop it when it's 0.49 or below. I want to let you know, though, that we're only going to do it one time at the end of the calculation. You're not going to be rounding up and down in between each piece, or you'll definitely end up with the wrong answer. So let's imagine we have this scenario of 26 amps, and after we do all of our math, it equals 32.5 amps. Well, in this case, we're going to round up to 33 amps. Now let's imagine we have a similar scenario, and when we get our answer, it's 31.25. Well, in this case, it's 0.49 or less, so we are going to round down in this scenario. And that's how we're going to deal with all of our numbers in load calculations. When doing Article 220 load calculations, we're going to be using nominal voltages. Although our actual meter reading might be 115 or 130, for our calculations, we're going to be using nominal system voltages like 120, 12240, 12208. It makes it a lot easier to do these calculations, not having to guess or wonder what the actual voltage readings might be. The first thing that we're going to learn about for our whole home load calculation is how to calculate the general lighting and receptacle loads. This is going to cover all of our general lighting and general receptacles in places like bedrooms, living rooms, hallways, everywhere that's considered a general area. We've grouped all of them together and come up with a very easy way to do it. Now, what I'm getting ready to teach you only applies to residential 1, 2, and multifamily dwelling units. Before we go any farther, we need to define and clarify what is a 1, 2, and multifamily dwelling unit. Well, a single-family dwelling unit, often called a one-family dwelling unit, is exactly like it sounds. It is a single standalone structure or classified thereof. Secondly is going to be a two-family. In our area, we call it a duplex. You may not use that terminology, but this is two homes that are smushed together and classified as a two-family dwelling. And anything that is 3 or more is called a multifamily dwelling unit. It's very important that we understand these definitions because there's some codes that apply in certain areas than others that we have to watch out for. Not only in electrical, but also when we get into building, mechanical, plumbing, and zoning. And these are universal across all these trades. There's a single family, a two family, and a multifamily dwelling unit. The first question we have to ask is, how do we calculate the general lighting load? Are we going to calculate it per receptacle outlet, per lighting? Do we have to count them, add it all up? Thankfully, no, they've made it very simple. So we're going to calculate it at 3 watts per square foot. So for all of the general lighting and all of the general receptacles, all we have to do is take the square footage of the dwelling unit and multiply it by 3. But the code language actually uses VAs. So 3 watts per square foot or 3 VAs per square foot. But the question is, what is a VA? A VA is a volt amp, and for all of our testing, it's equivalent to a watt. So it's true for us to say that 2400 VAs is equivalent to 2400 watts. So for these calculations, we're going to be calculating them at 3 VAs per square foot. When calculating our general lighting and receptacle loads, we will use the outside dimensions of a building or structure. So we're going to measure from the outside of the building, both directions, do our multiplication, and that'll let us know how many square feet we have to multiply by. When calculating our general lighting and receptacle VAs, open porches and garages are not counted in our general square foot VAs. We do not count garages, open porches, carports, and spaces that are not adaptable for future use. How many VAs would you calculate before demand factors? Now, let me stop right there. I haven't taught you what a demand factor is yet, so I'm not going to teach you how to apply it to this part of the load calc because it's really the most complicated, especially if you don't know what a demand factor is. I'm going to teach you a little bit at a time what a demand factor is, and by the time we round back around to teach you how to do it, you'll be a pro at it. How many VAs would you calculate before demand factors in a home that is 1,500 square foot of living space on the main level with a 500 square foot attached garage and a 500 square foot unfinished basement that is adaptable for future use? Step one is find what our total square feet that we're working with. So we have our 1,500 general, we will count it. Then we're going to omit the 500 square foot of attached garage. We're going to count the 500 square foot of basement because in this question, it is adaptable for future use. In your testing, it'll say either or, and in the real world, it's almost always adaptable for future use, but you can work that out with your local electrical inspector. So all we have to do is total all that up. That gives us 2,000 square feet. Then we take our 2,000 square feet multiplied by 3 VAs per square foot, and we're going to select D. Great job. How many VAs would you calculate before demand factors in a home that is 2,800 square foot of living space on the main level with a 500 square foot upstairs bonus room and 500 square feet of open front porch? First thing we're going to do is total our square feet. Of course, we're going to count the 2,800 of general, but what about this bonus room business? Yes, we will count the 500 square foot of bonus room. I want to note that the bonus room is a part of the general square foot, but the question makers will put things like this in your test to throw you off. Then we are going to omit the open front porch. We total all this up and we get 3,300. Now we take our square feet multiplied by 3 VAs per square foot, and we're going to select C. Now that we've learned about our 3 VAs per square foot, now we have to learn about what's called our small appliance and laundry circuit VAs. In every whole dwelling unit calculation, we're going to have 2 small appliance branch circuits calculated at 1,500 VAs each, and 1 laundry circuit calculated at 1,500 VAs each for a total of 4,500 VAs. Now, this is something that we're only going to do and attach it to the general lighting load and receptacles before demand factors. We're only going to do it when we're doing a whole house load calc. We are not going to add it on to something like an individual dryer or an individual range. Those are calculated individually. This is only when we're doing a whole home load calc. And once we start doing them, I will make sure to reiterate to you so you understand when and how to apply this. The easiest way to do it is anytime you're doing a whole dwelling unit load calculation is you take your square foot and you multiply it by 3 VAs per square foot. Let's imagine we had this 2,000 square foot house multiplied by 3 VAs equals 6,000 square foot. Then you just tack on the 4,500. It's for the 2 small appliance and the 1 laundry circuit. And you're only going to tack it on if you're doing a whole home load calc. All right, y'all, that's it for lesson 2. You can head over to electricalexamcoach.com to unlock the pro version and all of the quizzes and practice tests. Let's get to it. Hey everyone, welcome back. I am the Electrical Code Coach, and this is lesson 2.3 at electricalexamcoach.com. Today we're going to be learning about fixed appliances and how they work into a whole house load calculation. Fixed appliances include things like dishwashers in this picture, but it also includes things like garbage disposals, water heaters, central vacuum systems, and microwaves, and pretty much any other appliance once it's fixed. You'll notice in this bottom right-hand picture that there's 2 microwaves. One is not fixed, and the other one is fixed. And when you fix it to the wall or fix it so it can't move, either with plumbing or mechanical vents or anything else, it now becomes a fixed appliance. And there's a special way that they calculate them when doing a whole home load calculation. What it does not include is it does not include dryers or ranges. We're actually going to deal with those separately. So this includes all other fixed appliances except for dryers and ranges. Let's get to it. Before we dive into the calculations, let's learn about demand factors. We're going to be using them for the rest of the program. A demand factor is a multiplier that the code will use to decrease or increase the total calculated demand. The question is, will they use all 4 of these appliances at the same time? And the answer is no. So the code makers have made it so we can reduce the overall demand. Instead of just counting them watt for watt, they've made some multipliers that allows us to reduce the demand that we calculate. And remember, if we have less amps, we could have a smaller service. If we have smaller service, we could have smaller pipe, smaller wire, and a smaller overall cost of the job. The small appliance 75% rule works like this. Where 4 or more appliances are fixed in place, you can apply a 75% demand factor to the total calculated load of the appliances. I do want to note again that this excludes dryers and ranges. We're going to learn how to calculate those separately later in the program. So let's imagine that we have these appliances. And the question is, how do we calculate them all together to turn it into amps and later size our service, which sizes our wire and our pipe? What we're going to do first is find our total connected load. So we're going to go ahead and total all these up, and that equals 6,800. Then we're going to stop and check for demand factors. Step 1 in all load calculations is to get the total connected load. Then we're going to check for demand factors. And in this case, we can apply the 4 or more 75% rule. We take 6,800 multiplied by 0.75, and that gives us a new reduced load of 5,100 watts. And that's what we would take and add to our whole home load calculation. How many VAs would you calculate for a single family dwelling that has the following appliances: a 4,200 VA water heater, a 1,000 VA disposal, and an 1,100 VA dishwasher? First, we're going to find the total connected load. We total all that up, it equals 6,300 VAs. Now, we check for demand factors. In this case, we only have 3 appliances, so the 4 75% rule does not apply, and all we have to do is take our total. I do want to note that one of the 4 choices was as if you had incorrectly applied the 75% rule. In this case, because we only have 3, we don't apply any demand factor at all, and we take the total connected load at 6,300. Great job. How many VAs would you calculate for a single family dwelling in Dallas, Texas that has the following appliances: a 4,200 VA main water heater, a 3,500 VA additional water heater for the basement, a 1,000 VA disposal, and an 1,100 VA dishwasher? First, we're going to find our total connected load. We take and total it up, and it equals 9,800. Now, we check for demand factors. Sure enough, we have 4 or more fixed appliances, so we can apply the 75% rule. We take 9,800 multiplied by 0.75. That gives us a new reduced load of 7,350 VAs. I want to note that if you look at option B, it was 9,800, as if you didn't apply the 75% rule. You got to be careful. Oftentimes, they'll have one of the answers be as if you missed or added one of the steps that you shouldn't have. But you've been grinding, you're going to get it. I know you can do it. And we're going to select C. Let's get to it. All right, y'all, that's it for lesson 2. You can head over to electricalexamcoach.com to unlock the pro version and all of the quizzes and practice tests. Hey everyone, welcome back. I am the Electrical Code Coach from electricalexamcoach.com. And today we're going to be diving into dryer load calculations. We're going to be in section 220.54 and looking at table 220.54. Let's head there now. When we get to table 220.54, we're always going to read our black bold heading to make sure we're in the right table. Great, I feel like we are. We're going to start on the left-hand side and find our number of dryers. Then we're going to use a straight edge and come over and find our demand factor in percentage. I want to make an important distinction at this point in the program. You have to be very careful with these titles right here. Sometimes they're listed in a replacement value and it just says demand. And in other tables, it'll say a demand factor in percentage. And we've learned that that is just a multiplier. Section 220.54 lets us know that dryers must be calculated at a 5,000 VA minimum or the nameplate rating, whichever is greater. Now, let's learn what a nameplate is. Equipment nameplates. A plate mounted on the equipment or engraved in the equipment that is stating its voltage, amperage, horsepower, and or its wattage. Now, it may only have a few of these, but as we've learned in previous lessons, we can apply Ohm's law to find the unknown. Now that we're dealing with larger wattage appliances, we want to make something clear before we move on. We remember that 1 VA is equivalent to 1 watt, But what is a kVA? In our testing, it's the same as a kW, which is a kilowatt, which equals 1,000 watts. So it's true to say that 1 kVA is 1 kW for all of our testing. Now let's imagine that we have a dryer, and this dryer is a 5 kW. Well, it's also true to say that it's 5,000 watts. And at the same time, if they say that it was 5 kVA, it's also true to say that it's 5,000 VAs. Let's practice converting back and forth very quickly. Let's go from kVA to VA. So if we had 5 kVA and we wanted to go to VA, all we would have to do is take and multiply by 1,000, and that would equal 5,000 VAs. And the same if we wanted to go from VA to kVA, all we have to do is divide by 1,000, and it'll convert it over to kVA. You'll get very familiar with this and won't have to do any multiplying or dividing, but if you ever forget, that's all that you have to do. What is the total VA load you would calculate for one dryer with a nameplate rating of 4,500 watts? First, we find the total connected load. For this, we know that we have to do a 5,000 minimum or the nameplate, whichever is greater. So the 4,500 is gone and the 5,000 remains. Now, we check for demand factors. For this, we're going to head to table 220.54. And we're going to find that 1 through 4 dryers, it's at 100%, meaning that there is no demand factor. And we just select A. Great job. What is the total VA load you would calculate for one dryer rated at 5,200 VAs? First, we're going to find our total connected load. We know that we have to do a 5,000 minimum or the nameplate, whichever is larger. In this case, the nameplate's larger, so we're going to select 5,200. Now that we have our total connected load, we're going to check for demand factors. For this, we head to table 220.54. When we get there, we find that for 1 to 4 dryers, it's calculated at 100%. There is no demand factor. And we're going to select C. What is the total VA load you would calculate for one duplex with 1 dryer in each unit and a nameplate rating of 4,800 watts per unit? First thing we're going to do is we're going to find the total connected load. We know that it's a 5,000 minimum or the nameplate, whichever is larger. So the 4,800 is out and the 5,000 is in. Then we have to multiply it by our 2 units, and that gives us 10,000. Now we check for demand factors. For this, we head over to table 220.54. And we're going to find that 1 through 4 ranges is calculated at 100%. And we're going to select A. What is the total VA load you would calculate for an 11 apartment multifamily dwelling unit with 1 dryer per unit and a nameplate rating of 5,000 watts? First, we're going to find our total connected load. We know that it's a 5,000 minimum or the nameplate, whichever is larger. We take our 11 units, multiplied by 5,000, and that equals 55,000 VAs. Now, we check for demand factors. We head over to table 220.54. When we get there, we find the demand factor for 11 is 47%. So we take our original load, multiplied by the demand factor, and that gives us a new reduced load of 25,850 VAs. And we're going to select C. Great job. What is the total VA load you would calculate for a 17 apartment multifamily dwelling unit with 1 dryer per unit and a nameplate rating of 5,000 watts? First, we're going to find our total connected load. We're going to use 5,000 minimum or the nameplate, whichever is larger. We take our 17 units, multiplied by 5,000 each, and that gives us 85,000 VAs. Now, let's check for demand factors. When we get to table 220.54, we're going to find that it's a 47% base minus 1% for each dryer past 11. So what we do is first have to figure out how many dryers we are past 11. We have 17 dryers minus the 11 base, and that lets us know that we're 6 past 11. Well, what this code is stating is that 47% was our base multiplier, and then what we're going to do is minus 1% for each one that we are past 11. We were 6 past 11, so we're going to take our 47% base minus 6, and that's going to give us a new demand factor of 41%. Now, all we have to do is multiply. We take our original load, multiplied by 0.41, and that gives us a new reduced load of 34,850 VAs. And we're going to select B. Great job. That's the end of lesson 3.1. I want to encourage you and let you know that you're doing a great job and that you can do it. You can head over to electricalexamcoach.com to unlock all of the features in the pro version, including flashcards and practice quizzes. I want to let you know that I offer coaching 100% for free. All you have to do is just email me at electricalcodecoach@gmail.com. Let's get to it. Hey everyone, welcome back. I am the Electrical Code Coach from electricalexamcoach.com, and this is lesson 3.2 in our video series. Today we're going to be learning about how to calculate ranges and cooking equipment and how they fall into the whole house load calculation. We're going to be in section 220.55. We're also going to be in table 220.55. Let's get to it. When we get to table 220.55, we're going to read the black bold heading at the top of the table to make sure that we're in the right table. Then, starting on the left-hand side, we're going to find our number of ranges. 1, 2, 3, 4, 5, and so on and so forth. Then we're going to notice that there's 3 different columns. They're really in 2 different groups. It's column A and column B are grouped together under the demand factor in percentage column. And the reason that's so important for us to watch out is because column A and column B are multipliers. They're actual demand factors. But column C is a replacement value, and you'll understand more of what that means as we get farther through this video. Starting on the left-hand side in column A, this is when your individual range falls 3.4 or less kWs. In column B is when our ranges, the individual range itself, falls in between 3.5 and 8 3/4. Then column C is when our ranges are 8.76 through 12 kW. Then in the bottom left hand of the table, you're going to see some notes. And that's when we have a situation that doesn't fit into the normal table. And we're going to take it piece by piece. Let's get to it. How many VAs would you calculate for a 9 kW range in a single family dwelling? The first question we're going to ask is, what column does our individual range fall in? Well, ours is a 9 kW, so it's going to fall into column C because it's greater than 8.76, but not over 12. And column C is a replacement value. Now let's find our total connected load. On the left-hand side, we're going to find our number of ranges. In this case, it's 1. Then we're going to cross all the way back over to column C and find that our replacement value is 8 kW. Then, just to stay in practice, I want you to always be familiar with checking for demand factors. But in this case, in table 220.55, column C is a replacement value. It is not a multiplier, so we're just going to select C. Great job. What is the total VA load you would calculate for 3 kW ranges in a dwelling unit? First question we're going to ask is, what column does our individual range fall in? Well, ours is going to fall into column A because the individual range is 3 kW. So we know that we're going to be doing a demand factor. Now we can start from the beginning. First, find our total connected load. We take our 3 multiplied by 3 kW, and that equals 9 kW. Now we check for demand factors. We're going to start on our left-hand side of the table. We're going to find our number of ranges. Then we're going to come over and we're going to find our demand factor. And we find that the demand factor for 3 ranges in column A is 70%. Now all we have to do is multiply. We take our 9 kW multiplied by our demand factor. That gives us our new reduced load, and we're going to select B. What is the total connected load you would calculate for 2 3.2 kVA cooking appliances in a dwelling unit? First question we're going to ask is, what column does our individual range fall in? Ours falls into column A. Now let's find our total connected load. We take and multiply it out, and we end up with 6.4. Now, let's check for demand factors. When we do that, we start on the left-hand side of our table. We come over and find our number of ranges, and then we cross over, and we find that for column A, 2 ranges is 75%. Now, all we have to do is multiply. We take our 6.4 multiplied by our demand factor, and this gives us our new reduced load, and we're going to select A. Great job. What is the total VA load you would calculate for one 7 kVA range in a dwelling unit? First off, let's find out what column we're using. Our individual range falls into column B. Now let's find our total connected load.
Well, in this case, it's just one range, so the total connected load is 7. Now, let's check for demand factors. When we head back to our table, we're going to start on the left-hand side and find our number of ranges. Then we're going to cross over and find our multiplier. And when we do that, we find that it's 80% for one range. Now, let's do the math. We take our 7 multiplied by our demand factor, and that gives us our new reduced load. And we select C. How many VAs would you calculate for a 14.6 kVA range in a dwelling unit? Step 1, find out what column our individual range falls in. When we get to column C, we find out that it's only good through 12 kW. When it's over 12 kW, you have to use one of our table notes listed down below the table. In this case, we're going to be using note 1. Note 1 says that when you have ranges that are 12 through 27 kVA, what we're going to do is increase that column C value by 5% for each kW that we are past 12. Now that sounds really complicated, but I'm going to break it down piece by piece. Step 1 is find your total connected load. In this case, it told us to increase the column C value by 5%. So we start on the left-hand side and find our number of ranges, which is 1, and then we cross over and find the column C value, which is 8 kVA. It wants us to increase that number by 5% for each kW we are past 12. Well, we're 14.6 past 12. And what the code states is that you're going to increase it for each kW past 12 or major fraction thereof. That's just a fancy way of saying if it's 0.50 or greater, you're going to round up. If it's 0.49 or less, you're going to round down. Well, in this case, we're 0.6, so we're going to round up to 15 kVA. So we are 15, and we need to find out how many we are past 12. Well, to do that, we can do some simple math. We have 15. We need to minus the 12 base, and we have 3 left over. Then we need to take that 3 and multiply it by 5% for each one, which is a total of a 15% increase. We're going to take our original number from column C, and we're going to increase it by 15%, and that's going to give us 9.2 kW. The reason that I put the 1 in front of it is because that brought back the 8, and we increased the 8 by the 15%, and it gave us 9.2. And we're going to select A. Great job. What is the total VA load you would calculate for a 3 kVA cooktop and 2 4 kVA wall-mounted ovens in a dwelling unit? First thing we're going to ask is what column do the individual ranges fall in? Well, in this case, we find that it falls into column A and B. This question is very simple. All you have to do is treat the column A ranges individually, the column B ranges individually, and then total them together. So what we do is we find our total connected load. The column A ranges is just 1, so it's 3 kVA. The column B ranges, we have to do some math, and we end up with 8 kVA. Now, we check for demand factors. We head back to our table, and we start on the left-hand side for our column A ranges, and we find the multiplier for 1, and then we start on the left-hand side and find our number of ranges for our column B ranges and find the multiplier, and we're going to find that they're 80 and 65% respectively. Now, all we have to do is do the math. We take our column A ranges and do the math, take our column B ranges and do the math, but then we can't forget to total them back together, and we're going to select A. Great job. Hey everyone, welcome back. I am the Electrical Code Coach from electricalexamcoach.com. Today we're going to be calculating HVAC/CVAs for our heating, venting, and cooling. The only code that we need to be familiar with is 220.60, and that's talking about non-coincidental loads. Let me explain what I mean. Usually in a typical house, you're not going to be running the heating and the cooling at the same time. So the code has made provisions for our whole house load calc that we only have to count the larger of the two. Let's get to it. How many VAs would you calculate for an 18.2 amp air conditioner compressor with a 1.8 amp blower and a 10 kW heat strip rated 240 on a dwelling unit? First thing we're going to do is find our total connected load. Let's do our air conditioning first. We take our 18.2 amps and then we add it with the blower motor. That's going to give us 20 amps. Now to convert that over to VAs, all we have to do is multiply. 20 amps multiplied by the voltage gives us 4,800 VAs. Now let's do the heat.
We have 10,000 to start with, but then we need to add the blower motor. Our blower motor is 1.8 amps multiplied by 240. That gives us another 432 VAs, and then we total the two together. Now we check for demand factors. There are no demand factors on this, and we will just select the larger of the two, and in this case, it's going to be the heat. We select C. Great job. How many VAs would you calculate for a 28.2 amp air conditioner compressor with a 3.2 amp blower motor and a 6 kW heat strip, all rated 240 on a dwelling unit? First, let's find our total connected load. Let's do our AC first. We take our amperages and we add them together. Then we need to take and multiply that by the voltage to convert it over to watts. And we end up with 7,536. Now let's do our heat. We know that we had 6 kW to start with. Then we need to add our blower motor. We take our blower motor at 3.2 multiplied by the voltage, and that gives us another 768 VAs. We total those two together, and we check for demand factors. There are no demand factors on this part of the code, so we're just going to select the larger, and in this case, we're going to select the cooling. Great job. That's the end of lesson 4.1. You can head over to electricalexamcoach.com to unlock the pro version and all of the practice quizzes. I'm here anytime you need me for free coaching. It's electricalcodecoach@gmail.com. Let's get to it. Hey everyone, welcome back. I am the Electrical Code Coach from electricalexamcoach.com, and this is lesson 4.2 in our video series. Now we're going to learn how to apply the demand factor to the general lighting load. At the beginning of the program, we learned that it was 3 VAs per square foot, and we had to add on the 4,500 VAs for our 2 small appliance and 1 laundry circuit. At the beginning of the program, I did not teach you about the demand factor for this because it's kind of complicated at face value, especially if you don't know what a demand factor is. But now that we're this far in the program and you are very familiar with using demand factors, I'm going to teach it to you now. And for this one, we're going to head to table 220.42. It's a very important table in our load calculation process. When we get to table 220.42, we always read the black bold heading to make sure that we're in the right table. And it says demand factors for lighting. Now, you can ask the question, if this is the 3 VAs per square foot, well, it includes receptacles. And you are correct. We are allowed to use this table for commercial lighting or any of the lighting in the following locations that we're getting ready to talk about. But we're also allowed to use it for the entire 3 VAs per square foot, plus the 4,500 that we tacked on for the 2 small appliance and 1 laundry. Using this table, we start on the left-hand side and find our location. The first one we find is dwelling units. Then we're going to find hospitals, hotels and motels, warehouses, and really important down here at the bottom, it says all others. So if it's not listed inside of this type of occupancy, we're going to cross over. And if you look over here down in the bottom right hand, it's at 100% calculation, meaning that there is no demand factor for lighting unless you're one of these specific places that are listed on the left. Then over here across the top, we find our demand factor. In this column, it's the portion of the VAs. And then in this column, it is the demand factor in percentage. We're going to break this down one piece at a time and learn how we apply the demand factor to the 3 VAs per square foot and the 4,500 VAs for the small appliance and the laundry circuit. Let's get to it. When looking at this table, we're going to see a multi-layered demand factor for dwelling units. Step 1, we're going to take the first 3,000 VAs at 100%. Step 2, we're going to take in between 3,001 through 120, which is technically just another 117,000 more. And that's how I'm going to refer to it for the rest of the program. We're going to take that percentage at 35%, and then we're going to take anything above and beyond that at 25%. Then step 3, we add them back together. We take the original 3,000 that we set to the side. Then we're going to take that new reduced load, add those two together, and that's going to give us our total load. What is the total general lighting load you would calculate for a 1,600 square foot home, including the small appliance circuits and the laundry circuit in a dwelling unit after demand factors? I want to note that on your examination, they will not mention the small appliance and the laundry circuits. You just have to know that anytime you're doing the total general load or you're doing a whole house load calc, you have to tack on that 4,500 VAs. Step 1, find our total connected load. We're going to take our 1,600 square foot multiplied by 3 VAs per square foot, and that equals 4,800 general square foot VAs. Now we need to tack on our 4,500 for our 2 small appliance and 1 laundry circuits. Then we take that load and we check for demand factors. We head to table 220.42. We're going to take our first 3,000 at 100%. Then we're going to take that remainder at 35%. Then all we have to do is total the two back together. And we're going to select D. Great job. What is the total general lighting load you would calculate for a 1,200 square foot dwelling unit? Notice that I took out all the pointers that we had in the previous slide. Anytime it asks for the total, you're always going to be applying a demand factor if there is one. And in every one of these type calculations, you're going to have the 2 small appliance and 1 laundry circuits. Step 1, find the total connected load. We're going to take our 1,200 square feet multiplied by 3 VAs per square foot, and that's going to give us 3,600 square foot VAs. Now we have to tack on our 4,500 for our 2 small appliance and 1 laundry circuits. 3,600 plus 4,500 equals 8,100. Now we check for demand factors. We head to table 220.42. Step 1, we're going to minus 3,000 and take it at 100%. Step 2, we're going to multiply that by 0.35. All we have to do now is add them back together, and we end up with a new reduced load of 4,785 VAs, and we select A. Great job. That's the end of lesson 4.2. You can head over to electricalexamcoach.com to unlock all the quizzes, flashcards, and everything else that comes with the pro version. I offer my coaching 100% for free. All you have to do is email me at electricalcodecoach@gmail.com. Let's get to it. Hey everyone, welcome back. I am the Electrical Code Coach from electricalexamcoach.com, and this is lesson 4.3 in our video series. And today we're going to be tying all these pieces together that we've been learning about the whole home load calculation. We're going to learn how to take our general, our fixed appliances, our dryer, our range, our HVAC, and turn it into our whole home demand. Let's get to it. What is the total VA demand you would calculate for a 1,600 square foot home with the following loads? Now, I know this looks daunting, but we're just going to take it one piece at a time. You've worked very hard up until this point, and I know you can do it. I want us to get used to laying out all of our calculations like this. On our piece of paper, write general, fixed appliances, dryers, ranges, and HVAC, and we're going to fill them in one at a time. Step 1 is to find our general lighting and receptacle loads. We're going to first find our total connected load. We take our 1,600 square foot multiplied by 3. That gives us 4,800 square foot VAs. Now we add on our 2 small appliance and 1 laundry circuit, which is 4,500. That gives us this total connected load of 9,300. Now we check for demand factors. Step 1, we're going to take the first 3,000 at 100%. We're going to take that remainder at 35%. Then we take the 2 and total them back together. And we're going to put that over here on the right-hand side. Every time I want you to write it out just like this, add in each load, total them up, and you'll be on your way to doing the whole house. Let's get to it. Now let's do our fixed appliances. We have a garbage disposal, dishwasher, and water heater. Find the total connected load. We total them all up and it equals 5,500. Now we check for demand factors. There are only 3 appliances, so the 4 or more 75% rule does not apply, and we write down 5,500. Now we deal with our dryer in the same way. We find our total connected load. We know that it's 5,000 minimum or the nameplate, whichever is larger. Now let's check for demand factors. When we get to table 220.54, we find that 1 through 4 dryers are calculated at 100%, and we put down 5,000. Now our range. First thing we're going to ask is what column does our individual range fall in? Well, this one falls into column C, and column C is a replacement value. Let's find our total connected load. We start on the left-hand side of the table. We find our number of ranges, and then we cross over to column C, and it's 8,000. Now we check for demand factors. There are no demand factors on column C because it is a replacement value, and we write down 8,000. Great job. Now for our HVAC VAs, we're going to take the larger of the heating or cooling. First, find our total connected load. Our heating is 10,000, and our cooling is our amps multiplied by our volts, which equals 4,320.
Now we check for demand factors. There are no demand factors on this portion, so we're just going to select the larger of the two, and we're going to put down 10,000. Now all we have to do is total it all together. Now all we have to do is total all of our loads. Make sure that you push the equals button in between each addition. And the reason is sometimes when you add a bunch of numbers without clearing it out, it will mess up inside the calculator. So I'm going to do mine like this: 5205 plus 5500, and then I'll hit the equals button. And then I'll do plus 5,000, plus 8,000, plus 10,000, pushing the equals button in between each time just to make sure I end up with the right answer. Then I'm always going to double check my answer on these large calculations and make sure that I get the same number twice. We end up with 33,705, and we select A. Hey everyone, welcome back. I am the Electrical Code Coach. In this video, we're going to cover how to calculate your general circuit calculations. Now, these type questions fall into two different scenarios. One, they're going to ask you the minimum required 20 amp branch circuits. And then the other one that looks almost identical is when they ask you the minimum required general branch circuits for a specific size home. We're going to look at these piece by piece, and we're going to break them down one at a time. At a minimum, how many 20 amp branch circuits are required for a dwelling unit? Now, this is asking a very specific question. There is a code minimum of 20 amp branch circuits that are required in every dwelling unit. The correct answer to this is 5. It's going to include our 2 small appliance circuits, our bathroom circuit, our laundry circuit, and our garage circuit. Now, this is not to be confused with the type questions that are asking about general or lighting or receptacle circuits. These are the code minimum of the required 20 amp branch circuits in a dwelling. And the answer is 5. Great job. At a minimum, how many 20 amp general branch circuits are required for a 2,700 square foot home? Now, your question may not say general, it may say for lighting and receptacles. You can keep an eye out for that. But usually if they give you the square feet, that's going to be the red flag for me, that I'm calculating the general branch circuits. So how we're going to do this one, it's very simple. We're going to do it one step at a time. The first step is to take our 2,700 square feet and multiply it by 3 VAs per square foot, like we've learned previously in the program. That's going to end up with 8,100 VAs. Now what we have to do, because this is our general lighting, those are all going to be 120 volt circuits. So I'm going to take that 8,100 and divide it by that 120 volts. And that's going to give us 67.5 amps. I'm converting it over to amps. Then we're going to take that and divide it by whatever size branch circuit that we are going to be installing. In this case, they want to run 20 amp circuits, and that's okay. Here we go. We take our 67.5 divided by 20. That lets you know at a minimum for this home, you must have 3.375 circuits. And we're always going to round up because you can't have a piece of a circuit. So the correct answer would be 4 for this home. Now, these are not to be confused with the 5 required ones. This is if someone wanted to continue to wire their home for their general lighting and receptacles with 12 gauge wire. They'd be allowed to put them on 20 amp circuits at that point, and this is how we would calculate it. Now let's do a 15 amp version. At a minimum, how many 15 amp general branch circuits are required for a 2,700 square foot home? The first thing we're going to do is take our 2,700 and multiply it by 3 VAs per square foot. Then we're going to take that and divide it by 120, which is our circuit voltage. Then we take that remainder there and divide it by the size circuit, and in this case, it's 15 amps. It's going to equal 4.5, and we're going to always round up to 5. Now, there are other ways to calculate this, but for me, this is the simplest and one that works every time. And that's what I always want to be able to give to you. One, to me, that is the simplest and one that works every single time. You can head over to electricalexamcoach.com for more exam prep like this. Let's get to it. Hey everyone, welcome back. I am the Electrical Code Coach from electricalexamcoach.com. Today we're going to be diving into lesson 5.1, and it's called the optional method for load calculations. When I hear the word optional, I think either or, but this is actually a whole nother method for doing load calculations, and its name just happens to be the optional method.
Everything I've taught you up until this point is called the standard method. In the absence of a method listed on your test, you're always going to default to the standard method. And thankfully, you'll never get an optional method question unless it states the word using the optional method. It's so important that we know that. We're going to find all these rules laid out in 220.82. Specifically, we're going to be focusing in part B. It's very simple. It took me about 6 videos to teach you how to do the standard method. It's only going to take me 1 to teach you the optional method. We're still going to do our 3 VAs per square foot and our 4,500 VAs for our 2 small appliance and 1 laundry. Then we're going to take that and take the nameplate of all appliances, and we're going to apply 1 demand factor. Then that's going to give us our new reduced load. Now all we have left to do is total our HVAC. We're going to take the larger of the heating or cooling. We add that back to that reduced load from above, and we're going to have our total connected load. It's that simple. We're going to take it 1 piece at a time, and then we're going to put all the pieces together. Let's get to it. The optional calculations that we're about to learn apply only to a single-family dwelling unit. The optional method for a multifamily dwelling unit is very similar, just uses different tables and different demand factors in a little bit different way, and we'll learn all about that a little bit later in the program. Step 1 with any load calculation, whether standard or optional, is to get our general lighting demand. We're going to do our square foot VAs just like we did before. We take our square foot, let's imagine we have a 1,600 square foot house. We multiply that by 3 VAs per square foot. That gives us 4,800. Now we need to tack on our 4,500 for our 2 small appliance and 1 laundry, just like we did before. Now we total them all up. The only difference is that we do not apply any demand factors at this point. We're going to apply a general demand factor later. How many VAs would you calculate for a single family dwelling that has the following appliances? A 4,200 VA main water heater, a 3,500 VA additional water heater for the basement, a 1,000 VA disposal, and an 1,100 VA dishwasher. First thing we're going to do is we're going to find the total connected load. With the optional method, we're going to take the nameplate rating of all these appliances. Now, let's check for demand factors. There are no demand factors yet at this portion of the calculation. All we're going to do is total up all these appliances, and then we'll apply 1 general demand factor here in just a little bit. And we select B. Great job. How many VAs would you calculate for a 4,800 watt dryer in a dwelling unit using the optional method? First, we're going to find our total connected load. With the optional method, we're going to use the nameplate rating of all of our appliances. We check for demand factors, and there are no demand factors yet at this portion of the process, and we select C. How many VAs would you calculate for a 15 kW range in a dwelling unit using the optional method? First, find our total connected load. We're going to use the nameplate of all appliances. Now let's check for demand factors. No demand factor applied yet, and the answer would be 15,000. Now that we've learned to take our 3 VAs per square foot and our 4,500, and then to take the nameplate of all the appliances, let's learn how to apply the demand factor to this portion of the calculation. It's super simple. You just total all that up and then apply 1 general demand factor. Let's get to it. Let's imagine we have this imaginary load of 32.8 of general lighting and appliances. Step 1, we're going to take 10,000 and set it to the side. Then we take that remainder at 40%. Then we can't forget to add back the 10,000. And we end up with 19,120. It's that simple. Then all we have to do from there is calculate the heating, like we're getting ready to learn, heating and cooling. We're going to choose the larger of the 2, and then we total those 2 numbers together, and that's our whole home load calc. With the heating and cooling optional method, we still will choose the larger of any 2 of the heating and cooling listed in 220.82c. It's very simple. If you get an optional method whole house or an optional method heating or cooling, you just go down and read the prescription for each part. There are 6 different parts. It tells you what to do. It's very simple and easy to understand. And then once you've calculated the heating and the cooling, you just select the larger of the 2. What is the total VA demand you would calculate for a 1,600 square foot home with the following loads using the optional method? I want you to take a minute and write all these down. That way you can follow along as I go through each screen. It's very similar to our standard method question. It's just going to go a whole lot smoother and a whole lot quicker. Step one with any load calculation, whether standard or optional, is to get our general lighting demand. We're going to do our square foot VAs just like we did before. We take our square foot. Let's imagine we have a 1,600 square foot house. We multiply that by 3 VAs per square foot. That gives us 4,800. Now we need to tack on our 4,500 for our 2 small appliances and 1 laundry, just like we did before. Now we total them all up. The only difference is that we do not apply any demand factors at this point. We're going to apply a general demand factor later. Now that we've got our general, all we have to do is find the nameplate rating of all of our appliances. We have them listed out here. We total them together, and that equals 21,300 VAs. Total those two together, and now we're ready to apply our demand factor to this portion of the load calculation. We take our first 10,000 at 100%. We take the remainder at 40%, and we can't forget to add them back together. Now let's go do our HVAC. Now that we have our new reduced load, let's add in our HVAC. We're going to select the larger of the heating or cooling. We work all the math out, and clearly the heat is much larger. We're going to take and add that to the party. After we do, we're going to have a total connected load of 28,240 VAs. Great job. All right, y'all, that's it for this lesson. You can head over to electricalexamcoach.com to unlock the pro version and the unlimited testing center. We also offer our full program on USB drive and DVD, so you can watch it offline and without commercials virtually anywhere. It also includes the MP3 files of all the lessons, so if you just want to listen to them as you drive down the road or while you're on the job site, you can do that. You can check out all that in the link in the description below. Most importantly, I want you to know that I offer 100% free coaching in life and in business. Just email me at electricalcodecoach@gmail.com. I just want to see you guys win. Let's get to it. Hey everyone, welcome back. I am the Electrical Code Coach from electricalexamcoach.com. And this is lesson 5.2 in our video series. We're going to be in section 220.14, and we're going to be doing a good overview and a great foundation of commercial load calculations. Later in the program, if you'd like to do some more obscure, more rare commercial load calculations, you'll have the opportunity to do that as well. Let's get to it. How many VAs would you calculate for 7 branch circuits where each branch circuit was dedicated for signs and outline lighting in a commercial building? Step 1, find our total connected load. For this, we're going to go to 220.14F, and it lets us know that for each circuit, it's going to be 1,200 VAs per circuit. We have 7 circuits multiplied by 1,200 equals 8,400 VAs. Now, let's check for demand factors. Anytime you're doing commercial lighting, you're going to go to table 220.42 if you're in the 17 or the 20, or table 220.45 if you're in the 23. Same table, different title. And when we get there, we're going to start on the left-hand side of this table, and we're going to look for our type of occupancy. It does not mention a generic commercial building. It only mentions dwelling units, hotels and motels, so on and so forth. So if your area is not listed, you have to go down to the bottom to all locations not specified below. Then we cross over and find out that there is no demand factor when you're dealing with this type of lighting, and we're going to select C. Great job. There are 2 25-foot sections of show window lighting in a bookstore front in Johnson City. What is the branch circuit VA load that you would calculate? Step 1, we're going to find our total connected load. For this, we're going to head to 220.14G. It's going to let us know that it's 200 VA per linear foot. We take our 50 feet multiplied by 200 VAs each. That's going to give us a starting connected load of 10,000 VAs. Now, we check for demand factors. We're going to head over to that same table, and we're going to look for our type of occupancy here on the left. And we're not going to find it. We're going to find that we cross over and that it's 100%, so there's no demand factor applied, and we're going to select B. Great job. For commercial occupancies, what is the calculated receptacle outlet load per yoke? First, we're going to find our total connected load. For that, we're going to head to 220.14I, and it's going to let us know that it's 180 VAs per yoke. But the question is, what is a yoke? This is a yoke. Starting on the left-hand side, it's also a device strap. It's what holds all the pieces together. What this code is stating is that whether we have a single, a duplex, or even this old school triplex here, each one of those would count as 180 VAs each. Think about it as each gang counting as 180 VAs. So if I have a single gang box, it's 180 VAs. If I have a two gang box and they're both containing receptacles on each side, it would count as 180 VAs per gang, and so on and so forth as you went to 3 and 4 gangs. Anytime you're dealing with a device strap, whether it has 1, 2, or 3